So I see Renee and Tree. I do not see Mirren yet.
Good morning, Dave. I'm here.
Hey, Todd.
Hello.
Oh, you moved home offices.
In my wife's pink office.
Oh, okay.
Good morning.
Good morning.
How's everybody doing? Hi, Tree. Hi, Dave. Hi, Todd.
Hello.
Hey.
I'm recovering from COVID.
Oh, yeah. How are you feeling?
Actually better, but I'm in the Netherlands. So I'm visiting and it was really, really bad timing. So that's why my voice sounds terrible.
Oh, goodness.
Your voice sounds just great.
How are you?
I'm visiting Seattle. I'm happy. I'm fine.
Okay.
Ah.
For the last few days. Hi, Marika. Hi, Renee.
Good morning.
Hello. Good morning.
How are things in Seattle, Gunter?
So things are gray, wet.
They're wet. It's mid-June. It's supposed to dry out by now, right?
No.
Or maybe that's July. I don't know.
Yeah, exactly. Summer doesn't start there till July 4th.
When I packed my clothes, I'm like, all right, shorts and one pants. I'm like, oh, should I do done pants and one short?
Yeah.
And no, I mean, at some point, I almost wanted to turn on the heat in the house. It's that bad. When you're used to Colorado in the summer, it's
right.
A little bit of a shock.
Yeah, well, it's funny how many houses here don't have air conditioning because they don't need it.
Right.
And like, this is America without AC. Wow, I forgot.
So in Utrecht, where I'm at right now, the place I'm staying doesn't have air conditioning. It didn't even occur to me. Tomorrow is going to be the first really hot day. So it's going to be interesting. I'll see how it works because I just don't remember what humid heat feels like anymore. I've been in Colorado.
Right. Yeah.
Yeah, Alice just put in the chat. I was going to say the same thing. Growing up in Colorado, we didn't have AC. No one had air conditioning. It was, so but now almost everyone does.
So something cool is happening right now. I don't know if you guys are aware, but like they put on the news every morning, but there's one of the lowest tide in like several decades that's happening right now with a -4 coefficient because the moon is at the northest part of its rotation. So people are excited.
We don't get the tide forecasts here in Boulder.
What, there's no tides on the reservoir?
Our piddly little lakes and reservoirs.
Yeah. So I don't see Mirren yet, and she's like the second speaker. So
You can move Renee and I up if you want. That's completely fine.
okay, we might have to do that.
Well, yeah, Renee's here.
Yeah.
And I don't want to make him stay up any later than he's already staying.
Right. Well, and Tree's also
so. We are in the same building.
Yeah.
Technically on the same floor, only in different rooms.
Oh,
But
that's
it's
right. Oh, you're not in Asia anymore, Renee. I forgot.
No. I'm now in the Netherlands, so now it's not a problem. But I think the reason why Tree is saying is because we have a group barbecue outside in the garden.
Oh, there's Maren.
Hi.
Good afternoon, Maren.
Hi.
So good morning, everyone who's coming in. Let's wait maybe 2 more minutes or so and then get started with a brief introduction of the co-chairs and liaisons, so you know who to talk to if you have any issues or questions about the land ice or polar climate working groups. And then we'll get started with our talks. So let's start in 2 minutes or so. Okay, we have 40 participants already, which is fantastic. So I want to get started. The recording in progress. There we go. So this is the official start. Welcome, everyone. Everyone joining remotely from Boulder or around Boulder or all around the world. We have several people from Europe joining, for example, from other parts of the world. So that's really exciting. First of all, my name is Jan Leenaars. I'm assistant professor at the University of Colorado Boulder and also the co-chair of the Land Ice Working Group, along with Bill Lipscomb. And I'm going to chair the first part of the session here this morning. A few things to note. So there are three parts of our morning session here. We have a first part of 6 talks. Then we have a break. Then we have 3 more talks. And then after those 3 talks, we have a third and a very exciting part of our morning session, which will consist of breakout rooms. Now, we as co-chairs and liaisons have come up with a list of breakout room subjects, topics to discuss. And one of us is going to share a link to a Google Doc right now. There we go. Thank you, Marika. So if you look in the chat of Zoom, there is a link to a Google Doc, and that will have a list of breakout room subjects. Now we have, as you can see, a list of exciting topics, but if you think you're missing one of your favorite topics, you can see that there are 2 wildcard topics on the bottom. So feel free to edit or add any of your favorite topics, so we can add more topics as we run through the first two parts of our session. So let's get started here by first introducing our leadership of the Land Ice and Polar Climate Working Group. So Bill Lipscomb, I'm going to give the word to you, and then you can pass it on to Gunther, Kate, and then we can go to the polar climate. And if you have any announcements, please go ahead.
Thank you, Jan. Well, first, by way of introductions, I wanted to introduce Gunther Legge, the science liaison for the Land Ice Working Group, and Kate Thayer-Calder, the software engineering liaison. Also, I wanted very much to thank Jan Lennartz for his service as co-chair for, I believe, the last 6 years. Jan, it's been a great pleasure working with you, and thank you very much for your service. And also, I wanted to welcome Miran Vizcaino, who has accepted, thanks, Miran, who has accepted a 2-year term as the upcoming co-chair of the Land Ice Working Group. So thanks again to Jan, and thanks to Miran as well for stepping up. Marika, did you want to say a few words about the Polar Climate Group?
Sure. Hi. So I'm Marika Holland. I'm one of the co-chairs for the Polar Climate Working Group. And my other co-chair is Hansi Singh from University of Victoria. There she is. And our liaison, who fills both the science liaison and software engineering liaison roles, is Dave Bailey. So who's here at NCAR. So reach out to any of us. If you have questions about the group or, topics that you want to make sure we focus on, things like that. I also did want to mention that the discussion session today, which, you have the link in the chat for the topics. And so in addition to adding topics, if you want to note which group you are planning to go to, and if there's some groups that have no one interested, we might scrap them in the interest of a different group. But also to note that these breakout discussions are in part to inform our computing proposal, which we'll have to write at the end of this summer and submit in the fall. And so if you have particularly exciting experiments in mind that you'd like to run using Polar Climate or Land Ice Working Group resources, definitely this discussion that we'll have at the end of the session, you can bring those up, because we're always looking for exciting experiments for our computing resources. So this will in part feed into what we write in that proposal and what resources we end up with. So I just wanted to note that. I don't know if there's anything else that my co-chair or liaison wanted to say or anything else the Land Ice Working Group wanted to make sure we covered. Oh, one other thing, I don't have our code of conduct up, but I did just want to mention that, we do have a code of conduct. So everybody, please be respectful, share the air, and, give constructive feedback to your colleagues. So I guess if there's nothing else, we'll hand it back to Jan, and he'll be running the first set of talks for the session.
Thanks so much, Marika, and thanks, Bill, for the kind words, and condolences to Miran indeed. So Marika, I don't know if it's me, but I don't have editing access to the Google Doc. So it's, for me, I think it's impossible to add my own name or change anything. So if you can take a look.
Okay, I'll try to change that while the talks are starting. Sure. Sorry about that. I thought I said it correctly, but yeah.
Perfect. So let's get started with the science. So we have 6 talks, if I'm counting right. Yes, before the break. The first of which will be given by Renee Weingart about exploring high mountain Asia with VR CESM. So just for the speakers, let's try to limit your talks to around 12 minutes. So we have around 3 minutes for switching speakers and questions, obviously. For the audience, you can ask your questions in the chat, or you can speak up after the talk, obviously. And for the speakers, you can also answer any remaining questions in the chat after your talk, or of course connect to your audience after your talk in a virtual way. So Renee, without further ado, please, if you can share your screen and we can get started.
Yes.
And I will give you a 2-minute
Thank you.
warning after 10 minutes, just a vocal warning, so you know
Okay.
that the time is almost
Great.
up.
Great. Okay, I hope everybody can see my screen. Okay. Hello everybody. My name is René Wijngaard. Currently, I'm working at the Institute for Marine Atmosphere Research at Utrecht University. Here, I would like to present the final results of the VR CSM work in High Mountain Asia we did over the last 2 years while I was working in Korea. Just a short introduction on the High Mountain Asia VR7 grid. It's a grid with a regional refinement up to 7 kilometers over High Mountain Asia. We applied this grid in the following setup using CSM2 with CAM6, CLM5, and the no-evolve diagnostic community ice-sheet model. Further, we applied an elevation class downscaling scheme with 36 elevation classes, which is suitable for High Mountain Asia. Some statistics about this grid. We applied chem physics time step, 225 seconds. Dynamics time step is 18.75. And that eventually results in a model cost of about 90,000 core hours per simulated year. And if you do that on about 1600 CPU, you will end up with 10 years, model years in an actual month. We did eventually 2 model simulations. The first simulation was completed around 2020. And this simulation mainly followed defaults of CSM2 with exception of the maximum snow depth. We found out, unfortunately, that after this simulation that the surface mass balance was not that good. So that's why we did another simulation, which was completed at the end of last year. In this simulation, we did a more thorough spin-up procedure. We changed some parameters, for example, maximum snow depth in order to have a high refreezing capacity. We increased the ice albedo. We changed the rain snow repartitioning. Further, we did some tunings on the cloud cover, mainly in CLAP scheme and sea ice. And we included the Morrison-Gettleman 3 cloud micro physics scheme, which is actually the MT2 plus Kraupel. And further, we applied an updated glacier cover dataset. All the outputs are evaluated by comparing them with what we have in High Mountain Asia, what I could find. And that consists of graded outputs derived from the globally uniform 1-degree grids, reanalysis and satellite-based products, as well as RCM-based outcomes from related to glacier model. The first outputs I would like to show you here are for the 2-meter temperature. What we learn is that there are warm biases, mainly in summertime, and also in particular over the northern regions of subregions of High Mountain Asia. And these warm biases generally become smaller with increasing resolution. Contrast, however, in the southwestern region of High Mountain Asia, particularly there, we see cold biases, and those cold biases also become larger with increasing resolution. The pattern correlation also kind of demonstrates, although the pattern correlation are very good for every season, but you see that there's a slightly difference between the winter and the summertime, where summer temperature seems to have a better pattern simulation or result compared to watch forcing interim than in the wintertime. If we look into rainfall and snowfall, rainfall is overestimated mainly in summertime and in the monsoon-dominated regions, where the bias tends to be I think, yeah, the slightly larger for the 1 degree grid than for the high mountain Asia result simulations. And if we look at the pattern correlations are generally better for the high mountain Asia simulations, except for in the winter period. If we look at the snowfall is overestimated, mainly also in the southwestern region, which is could be linked to the cold bias, but also to some extent to the changed rain snow repartitioning. And if we look into the pattern correlation, particularly in summertime, there's a big improvement in the pattern correlation, and the same to some extent also in the other seasons. Then we move on to snow cover and snow depth. The snow cover eventually decided to compare it with the weekly snow cover extent of the NSIDC. And from those comparisons, we learned that the snow cover is slightly overestimated during wintertime, but in generally well, except for the northeastern region of high mountain Asia. And further, it's underestimated in summertime. We also see some improvements compared to the NE30, so the 1 degree grid, and that in autumn, generally the best match is there. If we look at the snow depth, we compare that one with JR55, which is generally the one of the better data sets in producing snow depth. So compared to JR55, we also see overestimations in the southwestern region, which also could be linked to the cold bias and to some extent to the snow model modifications. Then I would like to show you the glaciological surface mass balance results. In this case, we compared it with observation, so like the glaciological geodetical observations and RCM-based outcomes. In this case, it is WRF-based glacier model outcomes. And we see that the high mountain Asia VR surface mass balance is underestimated compared to those outcomes. We also see that there's a big improvement in the second simulation, and it's particularly in the southeastern region. The number of grid cells where a positive surface mass balance is simulated at the end of round triples from about 100 to about 300. And that's mainly also in the southern part of high mountain Asia. So that could also be probably a bit linked to maybe a slight increase in snowfall over there. And as already mentioned, the largest improvements are there in the southeastern part of high mountain Asia, as can be seen in the plot C on the right bottom side. One of the main reasons why there is also a big improvement is that in the updated glacier cover data set, we kind of also included glaciers that are located over 6,000 meter altitude compared to the former glacier that was kind of capped to 6,000 meter altitude. So that results in also a slightly more positive surface mass balance. And if we look at the coupler output, as is here, that goes into the ice sheet model, then we see that especially in the higher elevation zones, that there's even a positive surface mass balance. So that could also have contributed to it. But still, there's still some work to do. The SMB bias is still quite negative. And one of the likely reasons for that is that there's a cloud cover bias. I did not show that kind of figures here in this presentation, but we know that the cloud cover is underestimated over high mountain Asia, which results eventually in more incoming solar radiation and a smaller downwelling long wave radiation. So at the end, it eventually ends up in a higher net radiation at the surface. And that might eventually contribute to a warm temperature bias over Central Asia as well. Potential solution for that could be to notch CAM with ERA interim or ERA 5. Also, there's some missing physics. We did not take into account the effects of hill slope aspect and orientation. Could also be relevant, especially over high mountain Asia. About 27% of the glaciers are north facing, and there somehow topographic shading has some effect on the solar illumination. So it could be good, for example, to include a hill slope model, like for example the one of Sean Swenson. Also, for example, precipitation downscaling, debris cover is not included. And then lastly, there could be something related to the elevation downscaling in community land model. Elevation downscaling is currently only applied over glacier ice land units. And that can be a disadvantage, especially in grid cells with a very small ice fraction. Because as I see it, if you have a very small ice fraction, the other land unit will most likely dominate the signal or the grid cell mean, and the effects of elevation downscaling on the grid cell mean that goes into CAM is limited. And that is also demonstrated a bit in this figure, where I plotted the surface mass balance against the glacial fraction in several smaller elevation zones. And everywhere you look, you see that with a smaller glacial fraction, you have a more negative surface mass balance. And yeah, that's why I think it could be related to that. So probably to solve this problem, we also need to apply elevation downscaling over the vegetated land fraction as well. And further could be an idea to look into improving the the coupling between land and atmosphere subgrid heterogeneity. So like the clasp thing that is now done, I believe, by Megan Fowler. So yeah, this is a bit the summary of the talk. We see indeed that there are still some biases, but we also see improvements in the temperature and precipitation. The snow cover observation also shows some better agreement with the 1 degree grid. Snow depth is mainly overestimated, whereas we see that the first simulation shows a slightly better agreement than the second simulation, most likely due to the snow model modification. But I have to say that this is a kind of, how to say that? Now I cannot find the right word, but the idea is that JRA55 is also a model, and it's also based on observations that are there, but observations are quite scarce in high mountain Asia, so that makes it also a bit difficult to compare with. Anyway, the good news is that we can simulate a positive surface mass balance, but the challenge is that we still need to do a lot of work to improve the surface mass balance, mainly to tackle with problems with like cloud cover warm temperature bias, lacking model physics, and the elevation downscaling. And this will be actually my last slide for today. This is a bit about future or the current work I'm doing at EMAU. The idea is to work with bipolar VR grid with refinements to quarter degree over the polar regions. And the idea is to test a development version of CAM with 58 vertical levels and some modifications in CAM and CLOP, including the recently published CSM paleo calibration modifications. So that means we will end up with a lower climate sensitivity. And the reason why we need it is that eventually we also want to look into the future to see what SST or sea ice changes derived from storylines, how that will eventually affect the polar climate, or maybe even changes in the lower latitudes. So that's where I would like to keep it for today. And if you want to contact me, here are my email addresses. So are there any questions?
Thank you so much, Renee. Unfortunately, since you've almost used your 15 minutes of time, we need to switch to the next speaker. But if you have any questions for Renee, please put them in the chat, and then Renee can answer there in the chat. Also, while we're switching to the next speaker, Mira, please share your screen. Please take a look at the chat and the new link that Marika provided, where you can sign up for breakout rooms and or add new ideas for breakout room topics. So Miren, if you're ready to go for it, please do. Miren will talk about future deglaciation of the Greenland ice sheet using the coupled CSM to CESM 2. Go ahead, Miren.
Okay, sorry. Yeah, I was panicking with the mute. Okay, you can see my screen and you can hear me, right?
Yeah, we cannot see. Oh, we can now see your full screen and we can hear you. Perfect. Yep.
Okay, that's good. Okay, so I'm gonna discuss here the complete deglaciation of the Greenland ice sheet with a couple CESM, CISM. This is work mainly by Raymond Sellefall. It is focused on the coupling between the surface processes in Greenland and the climate. And other co-authors of this work are Michele Petrini and Sotiria Giorgio. Okay, this is a background slide with the current Greenland ice sheet mass loss. So it is contributing to sea level rise by 0.7 millimeter per year. And when we look at the projections in the last IPCC report, what you can see is that most of them are based on ice sheet models that are forced with the output of regional or global climate models. And in this case, we are missing the couplings between ice sheet and climate at all scales, no? From the global to the regional and the ice sheet scale. And on the other hand, we also have some coupled simulations, and in general, they have simplified processes, for instance, in the melt or refreezing calculations. So here, the added value of using CESM, CISM is that we are combining high detail with the coupling together. And the question that I am addressing today is how fast and by which mechanisms will the ice sheet melt under high greenhouse gas forcing. So this is going to be a 1% increase to 4 times CO2. And we already published the results up to year 350, and we are preparing the results from then until the complete deglaciation. And this is what I am going to show you today. So I'm going to organize the results in the climate simulation, the rates of mass loss and the pattern. And then I'm going to focus on the surface. And I will touch upon 2 items. One is the evolution of the precipitation, and the other one is the evolution of the runoff. Okay, so in these simulations, we apply coupling 1-to-1 between the climate and ice sheet components up to year 500, and from there we accelerated by 5. So we were using 1 climate year to force 5 ice sheet model years. So by the end of the simulation, we have a global warming of more than 10 Kelvin. And at the beginning, the Arctic warming is more than the warming over the Greenland ice sheet, but this changes after some time because the elevation of the ice sheet is going down, and then it warms more than the Arctic region on average. Okay, and the ice sheet is lost in 1700 years, which is very fast. And this is the pattern of the glaciation. Here you have the percentage at different years, and this percentage is the percentage of original area. So by year 700, more or less, we are at the half area than we are at year 1. And you can see that we are losing the southern part, and we don't leave anything there. And then the ice sheet is moving towards this location here. We are going to compare with this simulation by Somers et al. For the Imean. And here the pattern is slightly different. So there is quite some retreat going on in the southwest, but all this part in the south is kept. And on the other hand, there is much faster deglaciation from the north. So the forcing is completely different. In this case, is insolation forcing for the Imean. And in our case, it's a very, very high greenhouse gas forcing. Okay, here we are looking at the ice sheet elevation, the mean over the ice sheet. And so the thickness doesn't go down at the beginning because we are losing the low thickness areas at the margins first, but then eventually the thickness goes down very much. This is the mean elevation of the bedrock. So you can see how the ice sheet is retreating at the end at an area of relatively high bedrock. And you can see also what is the evolution of the how much is contributing isostasy, and it is very little. So it is 100 meters by end of simulation. And this very small contribution is because here everything goes very fast, and yeah, it won't make much of an effect. Okay, so this is the partition of the mass balance. Here is in the components of SMB, discharge, and basal melt. So please follow with me the black line. So when we are here in year 200, the contribution is 2 millimeters per year, and then we go to a maximum of 8 millimeters per year here by year 500. So the question is, what is causing this very strong acceleration here? So this huge increase in the contribution to sea level rise. So I'm gonna switch I'm gonna be focusing only on the surface processes. So we are gonna have contributions from precipitation and the contributions from runoff. So let's start with precipitation. The fraction of snowfall is decreasing from 90% at the end to 30% by the end of the simulation. Okay, these are the maps of how the precipitation is evolving. It is increasing all over the ice sheet. And here are the contributions from climate change, elevation change, and ice cover change. To determine those, what we do is we compare with a simulation that has fixed topography. So the precipitation is increasing both because of the climate change, but also because of the elevation change that we have. The contribution from changing location of the ice sheet is negative because the ice sheet is retreating from areas that have very, very strong snow, very high snow accumulation today, as the North Atlantic margin, the southeast of Greenland has very, very high accumulation rates today. Okay, so all of the increase of the precipitation goes to rainfall. The snowfall is practically constant. Here we are averaging the snowfall, and we are scaling by area. So we are dividing by the total area of the ice sheet. Because if we put total mass, the total mass is going to be going down because the ice sheet is getting smaller, and then we cannot distinguish processes. So we are dividing by area in these numbers here. Okay, so all goes to rainfall, all increase. The ablation areas, they are expanding very, very, very fast. So you can see that by year 1000, all of the ice sheet is ablation area. And in this period here, in between year 120 and year 200, we have a very, very fast expansion of the ablation area. How does this compare with ambient simulation? It's very different, because here we don't see that super expansion of the ablation area as a percentage of the total area of the ice. Okay, so these are the time series for the melt and the refreezing. So the refreezing, so initially is taking 45% of the melt, as the melt is increasing and increasing. So the refreezing increases first up to more or less the amount of annual snowfall rate, and then the percentage goes down. No? Okay, so refreezing works for a little while, and then cannot keep up with this.
2 minutes, Miran.
Yeah. Okay. Okay, so the contributions to the melt. So the elevation change is contributing a large amount by the end of the simulation. So it is by year 800 that the contribution from climate and elevation become similar. Incoming radiation, so the solar is going down, and the long wave incoming is going up. And if now we look at all of the fluxes, what we are seeing is that at the beginning, most of the melt is coming from energy of the incoming of the net long wave, but then the albedo feedback is kicking, and so the short wave radiation, the solar radiation, is dominating the contribution to melt, almost until the end of the simulation. And at some point, the sensible and latent heat fluxes become quite similar to the long wave contribution. Okay, so going into the shortwave, latent and sensible contributions, so they become very important when most of the surface reaches melt point, and then the atmospheric temperature continues to increase. So then we have a very strong temperature inversion close to the surface, and this is increasing very much the fluxes, except at the end of the simulation, when the winds go down very much, probably because the topography gradient goes down very much. Okay, so this is the summary slide. So what we have been seeing is that albedo feedback contributes very much to the melt, the elevation feedback as well. There is a very small contribution of the negative melt isostasy feedback to the whole process, because this deglaciation process is very, very fast, and the glacial isostatic adjustment goes slowly. And yeah, it is very fast. And from the snowfall, contrary to in comparison with other studies, we don't have major increases of snowfall. And something that we will explore more is that what is this reorganization of the turbulent heat fluxes of the ice is contributing to the melt very much. That's it.
Thank you so much, Miran. Any questions for Miran? Please unmute yourself. We have 2 minutes for questions. If no one has one, I have one for you, Miran. So you mentioned snowfall rates are not changing very much in the future. I'm wondering if the total precipitation is changing, in the sense that instead of snowfall, there is more rainfall. So the total precipitation changes, but the amount of snowfall does not increase very much. Can you comment on that?
Yeah, it is exactly as you are saying. So the total, so here, because the size of the ice is changing so much, we have to divide the gigatons per year by the area. Okay, and when we do that, yeah, so when we do that, okay, you would have to put these three lines together, you would have to add them, and this will give you the total change. But okay, let's focus on the so the elevation change and the global climate change are giving each 200 millimeter of increase, right? More or less. So all of it is going to the rainfall increase. And this is the line, for instance, for the climate related snowfall increase, and it is flat, it's around the 0. And for the snowfall is going, sorry, for the elevation contribution is going down. So as the elevation is going down, we are sending more to rainfall even. So even snowfall is losing extra. So all extra precipitation goes to the rain, plus something that is lost from the snowfall. Yeah. So rainfall is the winner here. Yeah.
Yeah. Great. Time for one more question. Hansi, you raise your hand, please. Speak if you can and want. Thank you.
Yeah. Hi, Mira. Thanks for that great talk. This is super cool work. So I guess my question is the extent to which these results are sensitive to the background climate sensitivity in the model. Just because this model is so sensitive, does that mean that if a model is more realistically sensitive, like this process will take like 2,500 years? Like I don't understand exactly how like the ice sheet dynamics and physics interacts with the climate sensitivity. And so it would be lovely to hear your thoughts on that.
Yeah, so it would be great to check that with a simulation where we can correct for the high climate sensitivity. Okay, so Gian, that I think is in the room, in the virtual room, I can tell you more about this, but what I am understanding so far is that this very high cloud feedback is more intense for warming over 4 Kelvin, which is what we have here. So these results very likely are much biased, so we have too much of warming. No? So this 10 Kelvin is too much for 4 times CO2. So maybe we can see these results not so much in the context of a 4 times CO2 simulation when we compare to other simulations, but we can compare them to other simulations with 10 Kelvin of warming to make sense of the time scale also. So there is an ice sheet only simulation that uses SSP 8.5 that melts the ice sheet within 1,000 years. So it is even a shorter, so it is by Andy Aswanden and colleagues. So there, I think they are working also with 10 Kelvin of global warming. So, and they are even faster than this. I think it is it is because there are some overestimations there for the lapse rate and also for the warming that is applied over Greenland. But yeah, so it is. We are not even the fastest with this. And it would be great to revise the results with a more adjusted climate sensitivity, yes.
All right, thank you so much, Miran. We're eating into the next speaker's time, so let's move on. If you have any more questions, please put them in the chat, and Miran, feel free to answer there and follow up. So the next speaker is Rajashree Dada. So Tree, if you're ready, and Miran has stopped sharing, so that's great. There we go. Smooth transition. So Tree is going to talk about, again, about the VR CESM2, but now applied to the Antarctic ice sheet. So Tree, the floor is yours. We can't hear you.
Okay, so better.
Now we can. Perfect.
Excellent. Okay. So I think Jan already covered exactly what I'm going to be talking about. I'm going to be evaluating the variable resolution CESM2, which over what I've been calling the ANSI grid, over the historical record, and this is from 1979 to 2014. This is with Jan Leonards, Adam Harrington, David Schneider, and Devin Dunmeyer. I'd like to thank NASA and the NSF as well for their funding and support. Okay, so to first introduce the grid, it's just right over here. This is a 1/4 degree resolution over the interior and 1 degree in a larger domain. And the outputs that we're going to be evaluating here from 1979 to 2014, but there are additional outputs from 2015 to 2021, which have moisture tagging implemented. These have forced SST and sea ice concentrations. So this is set up just like the AMIP simulations and uses CAM6 SE. And the cost right now for this version without the moisture tagging is 23,000 core hours per year. So we've also produced 3 hourly outputs for the atmosphere to facilitate the detection of atmospheric rivers, as well as from the surface in order to potentially force firn models. So one thing, it's an aside, it doesn't reflect very well here. An interesting factor of this grid is that actually the resolution towards the interior is in fact higher in the FV grid, 1 degree grid, just simply because of the way it converges. So there's an interesting case of where you're getting a lot of resolution over the ocean in particular, but not necessarily towards the center of the ice sheet. So we want to keep that in mind. So just to get a picture of what resolution means, at least towards the outer layer of the domain, this is over the Antarctic Peninsula where you have a lot of complex topography, and the SE points are shown in dots, whereas the 1 degree is shown in grid lines. So as you can see, it captures quite a bit more of topography. And the map on the right is the difference in surface topography of ANSI minus a 1 degree resolution. And you can see there's quite a lot of differences. And just for conventions throughout this talk, I'm going to be showing a lot of maps. It's always going to be ANSI minus the reference. And where it's gray, that means the standard deviations that are temporal for ANSI, and in the case of AMID ensemble, standard deviations do not overlap. So that's where it's significant. So going back to this, what main takeaway here is that you have slight lowering over ice shelves and a lot of resolution of topography, but a higher interior, and especially the peninsula. So the peninsula is going to come up in a second again. So the main question we're asking here is, what are the impacts of horizontal resolution alone, fixing everything else? And those are effects over the ocean as well as the ice sheet. And we're primarily focusing here on surface mass balance within the space of this talk. So what we're doing here is comparing these with AMIP runs over the same period using a 10-member ensemble, but these are with the 1 degree model. So what this means, we have the same forcing, the same physics, but just different resolution. And I don't know why that got cut off, but it's validated with ERA 5, as well as the Medley reconstruction, which uses firn ice cores to reconstruct SMB. And finally, with ROCMO 2.3, which is a RCM, a regional climate model at a higher resolution. So what I'm showing here is the difference in surface mass balance. Again, it's ANSI minus AMIP on the left side. And a lot of the differences can deform to topography, but what I want to point out especially is just the loss of SMB that's over here and how much of a change that is. But mostly towards the interior, you have a gain. Oh, towards the interior in East Antarctica, you have a really strong gain of SMB. Now, what I'm showing here in the purple and the green is, I'm going to take a second to explain this. It's how much of the bias where has the bias been reduced and where has it been increased? So when is it the case that ANSI is closer to the reconstruction or closer to ROCMO versus when has that diverged? And so in green is where the bias has been reduced, and in purple is where the bias has been increased in ANSI as compared to AMIP. And so we can see here is you have some pretty stark patterns, which is, towards this part of West Antarctica, you have some improvements in SMB, and that's mostly just where it's decreased. Whereas over East Antarctica, there's a little bit of a disagreement between the reconstruction versus ROCMO. So it's there's some dispute there. But if we look at the integrated SMB and surface melt, what I'm showing here is for the full ice sheet, for the grounded ice sheet, and for ice shelves, is surface mass balance, and with East Antarctica, West Antarctica, and the Antarctic Peninsula split up. There are kind of main takeaways here is that this is the standard deviation for the ensemble for ANSI. ANSI is shown in blue and orange is for AMIP. And most of the time, the the standard deviation actually overlaps, except in the case of the Antarctic Peninsula, or in most regions, over the ice shelves it does, but not over East Antarctica and not over the Antarctic Peninsula. And, and the other thing is, I'm touching on surface melt here just really briefly, but that's not the major focus of this talk. You have a lot more surface melt over East Antarctic ice shelves in particular. And that's kind of important. But the main thing is, even though you have a major increase in surface melt overall in ANSI versus AMIP, the difference between AMIP and the best case of observations that we have is that it's already pretty enormous. So it makes a already bad bias in AMIP a little bit worse. So the main reason, going back to the surface mass balance, most of this increase in SMB is driven by winter precipitation. So what I'm showing here is the SMB, first of all, and then the difference in large scale precipitation, the mean difference in over winter and over summer. And this is relative. So it's ANSI minus AMIP divided by AMIP times 100. What we can mostly see is two major takeaways here. One is that most of the precipitation is happening during winter and over the East Antarctic ice sheet, which matches up with a lot of this gain. And the other thing is I want to point out the wet LC sector. So this is some of the effects of enhanced topography over the Antarctic Peninsula. So you can see enhanced precipitation, to the west of the Antarctic Peninsula, and a loss of precipitation to the east. So that resolved topography actually counts for quite a lot. Now, what I'm showing here is taking a step back for that, and this is all during winter, is what are the sources of the moisture? Where is this coming from? So we know that there's a lot of precipitation in winter over East Antarctica. And so what I'm showing here is integrated vapor transport. And this is for meridional here and zonal here on the right. And the major takeaways here are that you have a lot of increased meridional transport over East Antarctica generally in ANSI, but that it's coming from sectors over here and over here. And I'll be piecing apart the winds in a second. But the other thing is that zonally, you have a lot more zonal transport that's occurring exactly where you have a gain and a loss in precipitation. So summer is a little bit less distinct, but I just thought I'd show it anyway, just to reinforce a couple of things. Is that you have a lot of the same pattern, and with a little bit with a lot more meridional transport towards East Antarctica in summer as well, but generally the effect is somewhat weaker.
2 minutes, Tree.
Sorry. So we're looking at, so I'm taking a step back and looking at this changes in circulation that drive that meridional vapor transport. And what I'm showing here, and so the vapor transport for winter is shown here. I'm showing as ANSI values for U500 and just the mean case. And then for V500, so this is, meridional transport towards the South Pole when positive. And ANSI minus AMIP, what I'm showing here is that there's been overall reduction in zonal wind, and this actually conforms more with ERA 5, but an increase towards on the continent. And so similarly, you can see this is a difference between ANSI minus AMIP meridionally, and you can see this increase in winds over here, which is helping to drive a lot of that vapor transport. But more interestingly, is that this one section over here where you're getting a lot of the vapor transport, this isn't a place where universally you've had a mean change in wind speeds. So that's something to piece apart in the future, is just to figure out exactly what conditions are creating that kind of a vapor transport. So now taking another step back and thinking of the changes in temperature. So ANSI overall has an increase in temperature at the surface. And I'm showing here ANSI minus AMIP on the right again, as usual. And as you can see, it's generally an overall increase in temperature across the board, except for some places in the interior and the wet LC sector to the east of the Antarctic Peninsula. And then this is, sorry, I didn't label this. This is in the near surface, and on the bottom is at T500, so at 500 hectopascals. And so what we can see here is that the bias is, increases a warm bias as compared to ERA 5. However, in the case of T500, it actually corrects a bias as compared to ERA 5. So taking another step back, I'm looking at changes of temperatures compared to AWS data. And there have been, so it's 133 AWS stations, and they're divided into bins from 500 meters to 500,000 meters to 1,000 to 2,000, 2,000 to 3,000, then greater to 3,000. And what we can see here overall is that it matches up mostly with the ERA 5 biases, except for the fact that this is, the 0 degree point, and where you have a positive bias, it's on the right, and when a negative bias is on the left. And in general, there's been more warming overall in ANSI, except for at very low elevations, which is kind of interesting. And in some cases, the bias is actually a correction. So, and this is particularly true in DJF. So previously, what was a cool bias has turned into, a slightly less cool bias. Whereas in winter, that bias is very, very strong.
1 minute, 3.
Whoa, okay. So I'm going to move on to the most interesting part, which is a change in cloud cover. What you have when you have increased temperatures is enhanced moisture and enhanced clouds. So the main takeaway here is I want to point you just to the bottom, which is enhanced total cloud liquid water path, which is much higher in ANSI. And in the interest of, and the effect is higher downloading net radiation. Since I'm going to lose time here and I can't go into the radiation budget anyway, the final thing I'll point out is that, okay, the main takeaways here are that higher surface mass balance in ANSI is driven primarily by enhanced snowfall in winter, and that these higher temperatures can lead to increased moisture, cloud cover, precipitation, and produce enhanced meridional moisture transport in East Antarctica. So the remaining question is really, where is that energy coming from? And is that energy coming from the ocean? And so we'll be examining the differences in the energy balance in particular to sort of answer that question. And thanks, and please feel free to contact me here, and my Twitter handle is here as well.
Thank you, Tree. Any question? We have time for one question for Tree while we switch speakers. No hands up. Okay, let's move to the next speaker. And if you have questions, please put them in the chat. And Tree, please feel free to respond there. Next speaker we have is Mira Berdau from University of Washington. Mira, are you ready to go? We can't hear you, but we can see your screen. That's a start.
All right, can you hear me now?
Yes.
Okay, sorry about that.
No worries.
Here we go. All right, can you see my screen?
Looks great.
Okay.
Go for it.
Yeah, so I'm going to talk today about some work I've been doing with the CESM model to explore ice sheet model sensitivity to thermal forcing. And this is work I'm doing with Günter Legge, Bill Lipscomb, and Nathan Urban. So this work was motivated by the results. Actually, let me just minimize this thing. Yeah, here we go. From a 2021 CESM ISMIP 6 paper written by Bill, Günter, and others, in which it became clear that some parameters that are chosen during the model spin-up actually ended up having a significant effect on the ice loss amounts during the forward runs. So for example, in the ISMIP 6 runs, the ice sheet is spun up by nudging toward observed thickness by adjusting basal friction and thermal forcing correction factor. So at the end of the spin-up, you get an ice sheet configuration that matches observed grounding lines and thickness, and it's a near steady state. So overall, the advantage of such a method is that it works well to keep grounded ice near observed thicknesses, but a disadvantage is that the parameters used during your spin-up can impact the sensitivity of the ice sheet during your forward runs. So for example, here are two final spun-up states that have used two different combinations of melt parameterization and calibration methods. And so each panel shows the change in thickness in meters between the final ice sheet state and the observations. So the positive values here, shown in the oranges and reds, indicate where the spin-up is thicker than observed. And the black lines indicate the boundaries of the floating ice at the end of the spin-up. So the thing to notice here is that both of these spun-up states look very similar, despite the fact that they use different parameters during their spin-up. So based on the previous work, there were two parameters that were found to be very important in the sensitivity of the ice sheet. First, gamma, which is a constant in the thermal forcing parameterization, and it describes how much melt occurs per ocean warming. So in other words, it affects the sensitivity of the ice to the ocean warming. So in the ISMEP6 experiments, for example, modelers were able to sample a low, medium, and high value of gamma as sort of a nominal exploration of the sensitivity of ice sheet projections to gamma. And they found that the choice of gamma had a significant impact on mass loss during forward runs. In addition to finding that gamma had a large impact, Bill's paper also showed that mass loss from the ice sheet was strongly dependent on the degree of water pressure support from the ocean. So the parameter P here controls the amount of water pressure support in marine-based ice sheets, and it therefore impacts the sort of the effective pressure near the grounding line. So in other words, it controls the basal slipperiness, particularly in marine-based ice. So in previous work, the parameter choices were found to alter grounded ice loss by a factor of 3 or 4, which means that the results of future ice strongly hinge on what spin-up settings you use. So we decided to explore this a little bit further. So first we ran a 25-member ensemble of spin-ups. So each run was 10 to 20,000 years long, and we generated combinations of P and gamma where we sampled more heavily toward higher P values and lower gamma values. And so the sampling is shown in the green with the P value sampling density on the y-axis and the gamma on the x. So the previous work had shown that there was less impact between P for 0 to 0.5. And then, so we decided to sample more heavily toward 1. And the gamma sampling density, is shown in the x, and it's weighted more heavily toward lower gamma values because that's considered more likely. And so the blue dots that are overlaid on top of the plot show the actual P and gamma combinations that we used in our spin-up ensemble. And then with this, we generated 25 different spun-up ice sheet states, which each come to look like the current ice sheet in terms of configuration, but they're all conditioned differently and will respond differently to future forcing. So from there, we forced each spun-up state with thermal forcings derived from the ocean temperature from 13 different CMIP6 projections under the SSP 585 scenario. And this results in 325 simulations. So here I'm showing the thermal forcing anomaly profile for the decade average from 2090 to 2100 as an anomaly with respect to the 1995 to 2005 profile. They're divided into regions following the Larmit basins seen in the bottom right map. And this plot shows the maximum thermal forcing profile with depth as seen by CESM. The thermal anomalies are ramped up linearly from 0 at the beginning of the run to maximum anomaly that you see here over the course of 100 years. And then we hold these constant for another 400 years. So we're simulating 500 total years into the future. So let's take a look at some of the results. The plot on the left shows the model mean sea level rise in millimeters over time. It shows that the warmest model produces the largest sea level with over 2 meters by 500 years into the simulation. And the coolest model results in about 75 millimeters sea level rise. And on the right, I'm showing the final sea level rise spread for each model. So remember, the spread that you see here is purely coming from the P and gamma value choices during the spin-up. So it appears that with sufficient forcing, such as in the EC Earth models, so those are like the pale purple and the brown, the choice of P and gamma can become quite important for multi-century sea level rise outcomes. And the simulations that are forced with the cooler ocean temperatures, like the BCC and CAMS, those little blue ones, they tend to show less sensitivity to P and gamma simply because there's not enough forcing to generate much sea level rise in the first place. So next, let's take a look at how the final sea level rise varies with the choice of P and gamma. So here I'm showing the final sea level rise values at 500 years into the simulation as a function of gamma in the top panel and as a function of P on the bottom panel. The linear fits are included here, and the R-squared values for those fits are shown to the right in the legend. So you'll just notice that the fits are very strong with gamma and less so with P. So in other words, on the continental scale, gamma has a much stronger influence on sea level rise than does P. So we can plot this a little differently to get a sense of the qualitative structure of the final sea level rise as a function of P and gamma. So every panel here is showing a final sea level contribution for different model forcing. And you should note that every color bar here is on a different scale. So on each y-axis is gamma, and on each x-axis is p. So even though the absolute magnitudes of the mass loss are different across each model, the qualitative structure of the mass loss is similar. And when we take a closer look, we find that there's a combined parameter space in which mass loss becomes significant. So specifically, we need p to be greater than 0.6 and gamma to be greater than 5 times 10 to the 6 in order to produce significant sea level rise. In other words, only when you have good hydrological connectivity and when melt rates are sufficiently high does a significant mass loss occur. And we've identified these sort of parametric thresholds that create such sensitivity. When we break things down by region, we find that the regions that contribute the vast majority to sea level in these experiments were the Ross and the Ronne-Filchner in the Weddell Sea. And this is due to high thermal forcing in most CMIP models in these regions. Here, I'm showing 3 examples where each row shows the results from a different model forcing. The sea level contribution for each P and gamma combination is broken down by each LARMIP region. And the first thing that jumps out is that the Ronne and the Ross are generally the regions that contribute the most. So basically, we're allowing warm water to enter these otherwise cold cavities. And so melt rates increase drastically, which we amplify with a high gamma value, and the mass loss can really take off. Interestingly, we don't see much contribution from the Amundsen in any of our CMIP6 force experiments. And we figure this is likely a result of 2 main reasons. First, the forcings generated for the end of the century by these CMIP6 models are fairly weak. They remain largely between 0 and 1 degree. And second, as part of the spin-up methodology, we assume the ice is in equilibrium with the current melt rates. And so in order to keep the ice from retreating under current conditions, we have to apply a thermal forcing correction factor that essentially cools the ocean in that region. And therefore, our future forcings must overcome this correction factor. And generally, that leads to an underestimate of mass loss in the Amundsen.
2 minutes.
All right. I'm just going to take a closer look at just one example case. So here I'm showing the ice thickness change for 2 simulations that are both forced with the same thermal forcing. So the only difference is the P and gamma values we chose during spin-up. So on the left, with moderate P and low gamma values, the ice sheet contributes about 1.25 meters to sea level, whereas with a high P and gamma, we contribute over 3 meters. So under the same forcing scenario, we see an almost 2 meter difference of sea level rise simply as a result of these 2 parameter choices. And one final thing I'll touch on before I wrap up is we did another set of experiments where we ran in an effort to better understand the thresholds in the Amundsen Sea. So we applied a synthetic thermal forcing anomaly of 1, 1.5, and 2 degrees to those 25 spin-ups. And the figure shows the sea level contributions under each experiment. So basically what we find is that the Thwaites, for example, Thwaites collapse is possible only when there is a partial to full water pressure support and when melt rates are sufficiently high. And we also find that in the Amundsen, this region exhibits a threshold of instability in the range of 1.5 to 2 degrees. So we believe this temperature threshold is likely associated with seafloor topography that acts as an obstacle to ice shelf flow. So our runs show that in the Amundsen, the grounding line tends to stabilize on a few high seafloor ridges, and under sufficient thermal forcing, the ice ungrounds and it enables retreat. Okay, so to wrap up, our study highlights the potential downstream effects of ice conditioning during model spin-up. And since it's possible to achieve a similar spun-up state with different sensitivities to ocean warming, it's super important to understand the effects of the most influential ice and ocean parameters. So we find that the combination of low basal friction near the grounding line, high sensitivity of melt rates to thermal forcing, and sufficient thermal forcing anomalies, mass loss becomes significant in multiple basins, and that these thresholds in the parameters tend to hold for all the basins. We find that the choice of P and gamma alone can impact the final sea level estimates by up to 2 meters. The Ross and Weddell regions dominate the sea level contributions in the CMIP6 force forward simulations. And mass loss in these areas is largely controlled by gamma rather than P, which implies a dominance of ocean forcing parameters on ice loss over ice sheet parameters. And finally, we find that the Amundsen exhibits a mix of ocean, ice, and temperature thresholds that together determine the sensitivity of the sector. The CMIP6 force runs fail to produce widespread waste collapse after 500 years. However, with additional synthetic forcing testing, we find that the Amundsen mass loss can be triggered with thermal forcing anomalies between 1.5 and 2 degrees. And in these cases, the grounding line retreats from topographic pinning points, and without these stabilizing points, the grounded ice in the basin collapses. I'll leave it there.
Thank you so much, Mira. Thanks for sticking to the time too. Any questions? No questions? Come on. All right. I'm sure there are questions. So if people process this a little bit more and have a question, please put them in the chat. And Mira, please follow up there. Okay, we're nicely on time. So let's continue with the next speaker, which is Jen K. Jen, are you there?
Yeah, good morning, all.
We're also very close to one another now. 20 meters
Can you see my
apart.
screen okay? Hear me?
Yes, go for it.
All right, great. I'm going to talk about work today that's been done by a postdoc at NOAA and Ceres in collaboration with myself and Tristan and Mike Steele. Clouds increasingly influence Arctic sea surface temperatures as carbon dioxide rises. So Anne was not available to make this presentation this morning, but was really excited for me to share the results with you all. I'm also especially excited to share these results because the original discussions about this topic came at a workshop that Mira organized about bringing together observations and modeling. I think it was in 2018, but Mike Steele and Tristan and I went to lunch and talked about these topics. And of course, this is just really cool what's come out of it. And so I want to thank Mira especially for organizing that workshop, which sparked these discussions. But this is Anne in the yellow here, recently presenting at a group meeting at CU. And if you have any questions about the work in detail, obviously I'll do my best to answer them, but also you can always contact Anne at the email that's listed. So the really basic motivation, and for this crowd, it's probably not at all news that in a warmer world with more carbon dioxide, the Arctic has more open ocean for longer periods of time. And relevant to this work, observations show that a larger maximum sea surface temperature, or SST max, occurs with an earlier date of sea ice retreat. And this was shown actually very nicely in a paper by Mike Steele and Dickinson in 2016, where they looked at the correlations between the maximum SST and the date of retreat. And indeed, they found, if you start retreating earlier, you have more time for the ocean to warm. And so the maximum SST that you reach is higher. And this paper really framed everything in terms of just the timing of when the sea ice starts to melt. And in particular, it was quite fascinating to us that they totally didn't think about clouds. And so why was that important? Well, clouds strongly influence radiative fluxes. So the presence of clouds, of course, can strongly impact the ocean heat gain during the melt season, and so therefore can influence the maximum SST. And of course, the influence of clouds is somewhat complicated because there's both the shortwave effects and the longwave effects. During the melt season, the shortwave effects dominate, so clouds would actually be, blocking incoming sunlight and leading to potentially a lower maximum SST. But it's important to acknowledge that the long wave is also important here, and so the exact seasonal timing, and it's not an easy thing to just pen and pencil. Like, it's really nice to have some observations or some models to kind of explore these topics. So the research questions that Anne crafted from this kind of basic introduction were, do clouds affect ocean surface warming in the Arctic? And if yes, is it through these long wave warming effects or the short wave cooling effects, or kind of what's the net balance of them? And also this very interesting question, do the impacts of clouds on seasonal surface warming and the SST max change with a warming climate? And so we started looking at these processes in observations, in particular from the CloudSat and Calypso, spaceborne radar and LiDAR, and other radiative flux observations. But we found actually that it might be nice to just have some idealized climate modeling studies to kind of look at these processes over a wider parameter space. So we set up some CESM2 CAM6 simulations. We just branched 3 100-year runs from the 1% increasing CO2 per year CESM2 run. So we have a pre-industrial run that's just continuing for 100 years. We have one that we branched at the present day or pretty close. CO2 concentrations, yes, actually next year we probably will hit 424 parts per million. So if you're thinking that's high, you should probably be looking up what the observed CO2 actually is right now. So it's pretty good for present. And then a 4 times CO2, so a much larger increase in CO2. And these runs are not in equilibrium, but they are increasingly warm and ice-free over the Arctic. And so they do provide a way to look at how these interactions between clouds, the date of ice retreat, and the maximum SST in the summer and into the fall occurs in the Arctic. And I want to highlight in particular that when we get to 4 times CO2, this is a quite modified state where we have, long period during the melt season where there's open ocean in the Northern Hemisphere. So just a couple of definitions, which we took from Steele and Dickinson. I think that they set this framework up really nice. So they talk about the melt season. So that's just when the sea ice is melting, and then the heat season. And so that's when the upper ocean is warming. So you can imagine this heat onset, there's maybe different ways to define it, but the way they defined it is the last day where you have sea ice concentration greater than 0.15. And the SST max, so the maximum warming, that occurs, sometime in the late summer, early fall, where the heat has all gone into the ocean and you reach the maximum SST. And then after that, of course, it's the descent into Arctic winter. So the SSTs are decreasing, and at some point, you form sea ice again. So this SST max and the heat season are really important because they're very related, right? This timing of how long you heat the ocean is going to affect how much the SST is. But then also we're interested in particular, how the clouds during this heat season affect this SST max. Yeah, just to kind of put our simulations in the framework of this heat season and melt season definitions, we have melt onset at the top here, the heat onset in the second row, and then the heat season length at the bottom. And you can see the heat season length, will depend on where you are spatially within the Arctic, but it of course is getting a lot longer as you get more CO2 in the atmosphere in these very idealized simulations. So, at 287 parts per million, it's just, weeks in the interior, maybe up to months at lower latitudes. But by the time you get to 4 times CO2, there's multiple months where you have open ocean. And the heat season is quite long. So a bit about the clouds in CESM2. This is just the seasonal cycle of liquid water path in these clouds. And then also the total cloud fraction from the Calypso simulator, which was embedded in all 3 of these simulations. And then we just show the Calypso observations, not because it's a perfect comparison to make to observations, but just to kind of show that, the seasonal cycle and the cloud amounts look pretty reasonable compared to modern day satellite observations. So these are all values for ocean grid cells polar to 70 degrees north. And I encourage you to check out a special issue paper from the CESM2 led by Ellen McGilhatton for comparisons of the clouds in this generation of CESM, so CESM2, and the last generation CESM1. And the basic point from the McGilhatton paper is that there's a lot more liquid in the clouds in the CESM2, and that's a more reasonable representation of the clouds than in CESM1. So if we're going to talk about how clouds affect the SSTs, it's important to understand that, of course, the cloud influence on radiation varies with season and with carbon dioxide. And so we can look at that as just a sensitivity of the change in the downwelling long wave on the top or the downwelling short wave on the bottom to a change in a cloud property. So for example, here, the sensitivity to a change in the liquid water path, or and on the right, a change in the calypso cloud fraction. And so you can see, the long wave is always warming. If you increase the liquid water path, you're always getting more downwelling long wave radiation. But the timing and the time of the year does depend on how sensitive things are. And in fact, you have a much stronger influence, especially in the winter and the non-melting seasons. And then, of course, the short wave is very tied to the solstice. And that's just because that's when you have the most downwelling short wave radiation. And so that's where clouds can block the most downwelling radiation. And so I want you to keep in mind, especially this timing where the short wave is really locked to the June solstice. And so as we can imagine, if we start to warm the Arctic and melt earlier, we're going to push this melt time and the heat season closer to this shortwave optimum for clouds to have a maximum effect. So some results. At low CO2, basically an early start to the heat season leads to a higher maximum SST. So this is basically the mechanism that was outlined in Steele and Dickinson. It makes total sense. It's negatively correlated such that, if you start earlier, an earlier day of the year, you're going to end up with a higher maximum SST. If we look at correlations with clouds, at both of these kind of pre-industrial and sort of present day, they're somewhat weaker than the correlations with the day of the year. So just the length of the heat season is really what's showing the strongest correlations. In contrast, as we start to see the heat season align with the June solstice, the clouds increasingly explain the maximum SST. And so we can start to see these correlations, especially between, for example, the heat season and the liquid water path and the maximum SST really start to increase quite a bit. And they actually become larger correlations than the actual length of the melt season or the heat season. So clouds are increasingly important for explaining this maximum SST.
2 minutes.
And the reason for this is just as already kind of motivated, the alignment of the heat season onset with the June solstice and the peak influence of clouds on shortwave fluxes. And this basically just gets optimized as CO2 increases. So here, for example, we can see these are just histograms showing when the heat onset occurs. And on the top, these same sensitivity plots, for example, the downwelling shortwave to the change in liquid water path. So you can see as we move into these reddish colors at the 4 times CO2, basically the timing of when the heat onset is starting to align with when clouds have their maximum shortwave cooling effect. So just a summary here, this is work in prep that Anne plans to submit to GRL very shortly, that with low CO2, it's the sea ice retreat timing, not clouds, that generally controls the maximum annual Arctic SSTs. As the CO2 increases, the sea ice retreats earlier, closer to this June solstice, and the clouds are increasingly explaining SST variability. And in particular, it is through the influence of the clouds on the shortwave fluxes. And this is just because of this alignment of the maximum sensitivity to changes in cloud properties with the summer solstice. And so just to kind of give you a hint at one of our key 3 points for the GRL Max paper, if we look at sort of the slopes of these correlations, we see that the seasonally free Arctic Ocean is 3 times more sensitive to clouds. So I will leave it there, and hopefully you will contact Anne if you have any questions, but I'm happy to entertain some here as well. And I want to thank also the Polar Climate Working Group resources that were used for this presentation. And again, to Marika for organizing the workshop that kind of started many of these discussions. So thanks.
Thank you so much, Jen. We have time for a couple of questions. I know that Paul Kushner asked a question in the chat. Paul, are you okay with?
Sure. Yeah, I can.
Question?
Actually, I probably have a more important question, but it was it was just that, and that was just to make sure I understood. So the 4 times CO2 simulations seem to be still equilibrating. So right, it seems like it's still warming up, and I'm wondering if, but it seems like your conclusions wouldn't really be sensitive to that. I'm imagining, right? Like basically you're just seeing a warmer climate as the ice free season gets sort of closer and closer to the solstice. You're going to.
We just wanted to hit it with a big hammer so that we could align those 2 times better. And yeah, I totally agree with you. Like, this is not necessarily like what's going to happen or a forecast for when this is going to happen, but more just like this is a physical alignment of 2 things, and they change as the climate warms. And so I think it's a really nice kind of process-based understanding of how these 2 things might change. And so when we might see this in observations, are we already seeing it in observations? We just wanted to kind of understand the parameter space before starting to look at observations to see for evidence of this, if that makes sense.
Cool. Yeah, it does. Thanks.
Marika?
Hi, Jen. Nice talk. I was just wondering how much the variability in the SST actually changes in these different climates. I mean, do you see it's much more variable in the 4 times CO2 climate, or just the magnitude of the variability? Do you know how that changes with the different climates?
Yeah, I would point you to Anne for details, but I can only imagine that with a longer heat season, you're going to be reaching larger maximum SSTs. And we're already seeing that in the Arctic these days, where I think, certain years, I think it's maybe, 2 or 3 or 4 or 5 degrees at the end of the melt season. And there is some sensitivity to, the start, of course, of that melt season in the current observations.
And so you'd expect the variability would increase with just the magnitude of the actual.
Yeah, you just have more time to heat it. And, I guess if it was a particularly cloudy summer, that would suggest that this would help, the clouds might help dampen how much heating you get. But I can only imagine if you're heating for months versus weeks that you're going to get warmer. Yeah.
Ed, please go ahead.
I had a very similar question to Marika, but I guess with a longer open water season, you just have longer time for the high frequency variability to give you low frequency. So I think. But I guess the other thing I thought about was, would your cloud variability itself change too, and would that increase? And I don't know that I have an immediate gut reaction for that.
Well, I do, because we've looked a lot at how summer clouds are sensitive or not sensitive to the underlying changes in the surface ocean. And in general, in the summer, there's very little cloud response to what's going on at the surface. So I would expect this is much more of just a top-down, clouds influencing the SST as opposed to a response. Now, a response to those SSTs being much warmer and that heat coming out of the ocean in the fall is definitely warranted. And, we've seen this through analysis of satellite observations in the present day record, and then also looking at future CESM simulations. And I'm happy to put those papers in the chat. They were both led by a former PhD student, Ariel Morrison.
Well, thanks.
Thank you, everyone. Thank you, Jen.
Yeah, thanks.
Let's move to our last speaker of the first session, but stick with clouds and sea ice. Xinghua Ding is going to talk about summertime atmosphere sea ice connections and the role of clouds in CSM and CMIP6 models. Please go ahead.
Thank you. Yeah, I hope everyone can see my slide right now.
Yes, perfect.
Okay, thank you. So yeah, this is the work led by my student, Ray Law, and other collaborator from like the GFDL and UCSB and PNL, and also some institute from China. So the main goal of the study actually is to look at something like we call the air atmosphere sea ice connection in the polar region in summertime, in the Arctic in the summertime. And when we talk about like the air sea coupling, normally we focus on like the tropical region, like related to the ENSO or IOD. But I think that this is still very new phenomenon in the Arctic region because we don't really know how these two components talk to each other, which influence another more. So to start this, we look at the observation first. So this is ERA data. To the right, you can see to show this result, basically we're just using the monthly ICIA sea ice area index for each month, like a pan-Arctic CS index for each month, and correlated with this zonal mean potential high, and in the Arctic region from 60 north to 90 north, zonal mean component. So by doing this, we try to see doing different like a lead and lag. We want to see which variable lead another variable more. So you can see very clearly if when the June Z lead like the other months, like the sea ice, you see very significant negative correlation. So negative correlation means like the warmer warm air or higher potential high lead CS decrease in the following months. And when the sea ice somehow can occur with the potential high or lead potential high, that means the CS may have a play as a forcing for the following Z change. We don't see clear like a correlation. So that means from this test, we can simply understand probably during summertime, that atmosphere influence the CS more easily rather than the other way around. So because this is so simple to calculate, we just using the September sea ice like this month, correlated with the JJAZ zonal mean as like a benchmark or like the pattern to evaluate the how CMIP6 model and the CSM capture a similar feature. And dynamically, we think that probably this is related to something we call this is the some like the atmospheric impact on sea ice through this adiabatic warming, because we know in the Arctic when there is a high pressure, normally it's a barotropical structure, and this one can induce this adiabatic warming, and due to this surface friction, and warm air can in the troposphere can emit increase a long wave radiation to melt CS. So somehow this is the idea. I think that behind this is a correlation pattern. And yeah, as I said, this is so easy to use to calculate the pattern. Just a September sea ice Arctic index correlated with the JJ zonal mean. We try to use this to evaluate all other available model in CMIP5 and CMIP6, and also a large sample archive. We find that if you do the same thing, no matter it's the historical one or like the pre-industrial simulation, we find the correlation with the coupling strength or connection strength is pretty weak compared with observation. In observation, it's a negative 0.6. Because it's detrended data, we do the same thing for all the model result. Same length for 40 years or 100 years or whatever length we use, we always find a much weaker connection between the two variables compared with observation. CMIP6 seem to be worse than CMIP5, and the CESM large sample is pretty good compared with the others for model in this large sample. And we also looked at CSM2, very latest version of the CSM2, different version. It's a little bit different, and it seems to like this negative center shift to the lower latitude. So it seems like it's important. If it's real, I think it's real because we find it's a very robust connection in observation. And if this is real and indicates some physical meaning, and I expect to see model should capture this because this is the pathway for the two component atmosphere and CS talk to each other, right? And if we want a model to have some skill to do like the future prediction, a future projection or CS prediction, we want CS can sense the change in the atmosphere. But right now it seems like these two components cannot talk to each other very easily on this time scale. So we try to understand why. And because we know this the long wave radiation is a key component, so we just simply do this, we call it partial correlation of this analysis. And very easy to understand. So just like the same plot, but we just do the Pan-Arctic average, just like the average from 70 north to 90 north. And we're using the number to show there's a connection. So you can see reverse sign, right? So we can see JJZ and the September sea ice is pretty strong correlated, 0.6. And the Mira shows same thing. And the model is weaker, but still can capture some strength. And then we try to remove, to simply do this statistical partial correlation, remove an impact of QNet and each component of QNet. What we want to say is that if a correlation drop really strongly, so that means that term is important. And you can see if you remove some impact from like latent heat, sensible heat, shorter wave, and doesn't change too much, it's a stress. But once we remove the clear sky, DLR, long wave radiation, and the total is just a substantially drop to something like this. And if you remove QNet, it's no connection almost. So this means that this connection is through QNet, but within the QNet, it's more like a DLR, especially clear sky DLR is important. And so now we just try to, the model do the same thing, even model the total stress is weaker, but remove the DLR effect from model relationship model also, this connection in the model is also dropped fast to almost like a neutral. And so now we think that we should focus on how the circulation linked to this DLR. DLR is like a JJ ADR in the surface. And we find even ERA5 and the Mira show a little bit different structure. This is simply just a JJ ADR at Pan-Arctic, just a 70 to 90 north average. Correlated with the Xonoming Z, you find something like the high pressure here and warm air emit long wave radiation. But the Mira show a little bit different structure. So now we're using the CESM model, 33 model to redo this, to recalculate this plot. And we find using SOM method to do this clustering. And we find basically all the performance can be represented by these 6 nodes, or we call 6 groups. And some is really weak, 0.3, some is really strong. And if you look at the detail of each group, you can find in node 6, that's what we call the strong group. And CESM Welcome is over there. And another one, you can see very interesting, some model different name, but they're using CAM as their atmospheric component. But the other 3 model, it seems like, or 2 model using like a match, a hot center model. I don't know why that, but I think that maybe this indicates this group model have some same physical component. Another interesting thing is that aerosol is all prognostic aerosol, but the model 1 is this group is like the prescribed aerosol and very different various atmospheric component. And the CSM2 is over here, CSM2, another version over here, over 4. But YCOM seems to be good to capture this one. And so then we focus on the individual component of DLR, and we separately calculate the correlation between the clear sky DLR and the cloud DLR with each variable. So this is a pretty busy plot, but basically just show the correlation of this one in JJA in over the Pan-Arctic, correlated with the Xonoming Z, Xonoming temperature, like the vertical structure, and just with the humidity and omega. And separately. So the first row is the total DLR. And this one ERA, the first column ERA, Mira, all the model, same 6 model, the good group and the weak group. The goal is to see how each atmospheric variable connect to the different component of DLR. So we find it's pretty clear, the clear sky or model reanalysis are pretty consistent. And the main troublemaker for this, the connection is a cloud DLR. And even it's opposite. So in the strong group, it's like the increase here, but in the weak group, it's a decrease. And so the weak group really similar to something in the Mira, and the strong group really similar to the ERA5.
2 minutes.
So, okay, so this is the idea. And we also looked at the cloud structure. Its basic idea is that ERA, if you're using the cloud DLR correlated with the cloud cover structure, is out of phase, and the Mira show in phase. We also looked at different cloud data. We find this cloud data, the better cloud measurement is the most similar to the Mira 2 data. And if you look at Z, like the upper level Z, same place, and the correlated with the Xonoming cloud cover structure, it seems like the high pressure favor out of phase change of the cloud, and the Mira show the in phase. And this is really similar to the strong group in ERA, and the weak group same like the Mira 2. And we think that this relative humidity is the key thing, because so we just zoom in here and look there's a domain average correlation between the Z and each relative humidity and the cloud. We find the same thing, just like there's a cloud cover change is mainly determined by the relative humidity. And to summarize this, I think the main idea is pretty simple. Just when there's a high pressure, the strong group, the model responds in two different type of regime. And the strong group really similar to the ERA5. And because the cloud is out of phase, so this can cancel this cloud forcing. So make this a total DRR. A clear sky DRR is more dominant in determining this. A total DRR. So that's the reason why circulation can easily talk to sea ice. But here is the uniform decrease. So this decrease DRR cloud forcing and cancel somehow here, make the total DRR is not as strong as a strong group. So that's probably doesn't favor this talking between the circulation and the sea ice. So this is the last plot, and I want to show here is that, so we speculate probably the easy reason to understand this is that probably due to circulation forcing not as strong in this of model historical simulation or pre-industrial simulation. So we just probably due to this teleconnection is not well simulated in the model. If you can see here, you have a really strong standard deviation of JDAZ, and the model generally is a little bit weaker. And that means the wind is not strong as observed. So then we just put observed wind. We put this ERA5 wind in the model, and we don't change other things. And if you do redo the same simple correlation, we find that the coupling is pretty close to observation. So that's CSM2 we can find also enhanced. So this means the physical part is okay, but just probably one reason is that the wind is a bit weaker in the model. So I want to stop here and take any question. So, oh yeah, one more thing I want to add is that the CAM can capture this well, probably due to this CAM system using like a relative humidity as like a threshold to determine this cloud formation. Yeah, this is our speculation. So we will do more to understand this feature. Yeah, thank you.
All right, thank you so much.
Oh, I want to stop.
Any questions? Jen, yes, go for it. You're muted, Jen. Sorry.
Yep. Hi, Jim. It was interesting to see what you're analyzing and looking at. I guess I have a couple of questions that are questions about methodology. Like, first, I'm a little bit concerned about making comparisons between CESM and clouds in reanalysis, especially when you're making no effort to make sort of a definition-aware, scale-aware comparison between them. I mean, the clouds in reanalysis are not all that different than the clouds in a climate model. They're heavily parameterized, and the radiative fluxes are not even constrained in the reanalysis. So I guess I'm a little bit skeptical about some of those comparisons. And maybe that's just a comment, and I'll stop there. Then I do have a question. So in these last comparisons that you were making with the wind nudged runs and the large ensembles, are you looking at the full large ensemble spread when you're making those comparisons? You're not comparing to the ensemble mean, are you? I'm a little bit concerned.
Yeah, that's a good question. I really appreciate that. We do each member and add them together. So there's some spread, but the overall is relatively weak. Like the average rate just like a 0.3. In observation is around 0.6. And some member can reach to the 0.4, but some member go to 0.2. So add them together is a 0.3. So we do each member first, then average them.
Yeah, so I don't think you should be averaging. I mean, obviously, if it's a 1 in 100 chance, it's probably not a good idea to say that the models are matching the observations, but we live in one reality. So we really only need one member to look like the observed winds in order for us to,
I agree.
So I don't know you should be doing any averaging at all. Am I wrong?
Yeah, so we should find a better way to show all the performance. Yes, we show standard deviation bar, but even the maximum one cannot reach to the observed the level.
Okay, I just recommend maybe a different way of visually presenting that, because that was like totally not clear from what you showed. Thanks.
Okay. Thank you. Yeah.
Ed, did you have a question? I think you raised your hand and then lowered it again.
Yeah, again, it was quite related to Jen's, but yeah, Chingwa, very thought-provoking talk. But I did actually, thinking about this, comparing like 40 years in observations with one of your earlier slides, actually, forgetting about clouds and just looking at the relationship between geopotential height and sea ice. And I think you showed like different CSM2 versions. I don't know how many years you were using, but how robust basically are 40 years, right? And I think maybe with a long control model, you can take a running 40-year windows. And I know we've talked about different, some of this teleconnection work, right? But Dave Bonin and I had that GRO paper, right, that some of the models can capture the observed teleconnection, like this is not the Pacific Arctic one, for over 40-year periods, but never with the mean state. So I would invite kind of that perspective too with this work, and maybe like split the observations, the first 20 years, second 20 years, and you know, try and get a sense of how robust this is. I think would be good.
Yeah, thank you.
All right.
I'd love to talk more about it. But
yeah, for sure.
Everyone, yeah, and Paul, I think your question was very similar to Jen's and Ed's, but feel free to continue in the chat. Yes. Thumbs up. All right, so it's time for a break. Thanks to all the speakers and to all of you for your interest and sticking to the time and very interesting science that we've had so far. We will reconvene using the same link, so this link will stay active in around 25 minutes from now, so at 10:40 Mountain Time. And then we'll see each other again. Maybe someone can repost the link to the breakout sessions. So if you haven't put down your name in one of the breakout sessions and you're interested in joining one of them, please do as soon as you can, so we have a view on the interest for the specific sessions. All right, thanks so much, and we'll see each other again in 25 minutes.
One thing I just wanted to say about the breakout sessions, sorry, is that Todd will not be assigning you. You will have to go into your breakout session. So this is just, you know, like a statement of maybe you're interested in those, but, you know, even if you don't get to write your name under one of those sessions, that's totally fine. We're going to basically put notes in there regarding perhaps some research priority areas and model experiment proposals. So yeah, I just wanted to clarify that. Thank you.
Hey, I have a question regarding this hike that's supposed to happen this afternoon. Is anyone actually going on it?
I'm not able to go, so.
Yeah, I just want to make sure if I want to hike by myself, I don't really need the CESM group, right? So I want to see whether anyone actually goes who's here. Who goes?
Maybe we could ask people to write to Uta if you're planning to go.
Well,
I'm not able to go either.
Yeah, I know you're not going because of the dentist, but yes. Yeah, I can put a question in the chat if anyone actually goes.
Yeah. I'll also just say we are planning to have this Zoom link open after the meeting adjourns, if people want to just stick around and eat lunch together and chat. So we kind of have an informal, just, you know, hang out together session when the meeting adjourns. And I figure people will probably leave for 10 or 15 minutes, get lunch, et cetera, and hopefully rejoin. So I guess enjoy your break. See you at 10:40.
Hi, Udo, you have a question?
Hi, David. Is my hand still up? I should have probably taken it down.
Okay.
No, I was just wondering whether anyone actually goes on this hike this afternoon.
Oh, yeah, I'm not sure. A number of us are going down to the Southern Sun around 4, so I'm going to pass on the hike myself.
I see. Yeah, I'm not sure. I mean, it's kind of hot. I know Bill and Gunther aren't coming. Marika said she's not coming. Only local people can't come.
Right.
So, I mean, it's a good idea to at least see people.
Sure.
So, yeah. No, just wanted to get some feeling for what's happening here.
Yeah, yeah. No, good thought.
As NCAR is still doing everything online. But maybe that's the right thing to do. I led the ISAT2 science team meeting in person, and sure enough, I got COVID.
Right.
So
yeah, I think this meeting was big enough that NCAR was concerned about us having an in-person element, and so CoCon had to declare it completely virtual. So
right, yeah, it's hard to see. We had ours hybrid. It was about 60 people in person and a similar amount online. I made sure all the lunches were eaten outside and we didn't go to a restaurant, just sort of to outdoor locations.
Right.
Yeah, like the Rayback where you stand around.
Yeah.
But yeah, oh well.
Okay. Alice pointed out that it's partly because we were not in the green phase, also in time for us to be able to declare. I think there was some uncertainty too about rooms available. Anyway, yeah, whatever.
Yeah.
But
now I had a meeting room like big enough so people could sit 6 feet apart if they wanted, but whatever.
Exactly.
No one else got sick, just I did. And no one else declared they got sick.
Okay.
Well, we'll have to see you at some point.
Yeah, well, as I said, we're doing the happy hour. Some of us are going to a happy hour at 4 at the Southern Sun.
Today,
yeah.
Okay.
And then there's the Madison AMS Polar meeting that's on track to be in person. So
what is that? Is that also
second week of August?
Yeah, I'm not sure. Go to Madison. We have the Arctic Sea Ice campaign coming up, which is in July, to be flown by the ISAT2 project. So I'm sort of involved in that.
Okay.
That doesn't really overlap with Madison if it's in August, but
right.
Yeah, not sure. It's difficult to plan anything whatsoever.
Yeah.
But NASA program management wasn't going to have it with all online anymore. So then folks didn't want to travel to Texas. So then I said, well, we can have it here. But in the end, the people who were most concerned didn't come here either. Oh, well. So, yeah, I mean, it's good to at least doing it online.
Well, it's nice because it does allow European speakers to join us and things like that. So, but I mean, there is the time difference, of course, but it's still, it still does add for a flexibility in a wider audience.
Right.
So.
Well, the last hybrid meeting wasn't that bad either. NCAR has these really nice room facilities in this new center.
Right. Right.
Well, maybe that was for the smaller meeting. And
yeah, I think we're set up for doing smaller meetings, hybrid, not so much larger meetings yet. But
okay, what else is new while we chat?
So, oh, not too much. So, but we're all keeping busy. Should be an interesting session on actionable science this afternoon. So,
right.
so you can probably put down your hand, Uda.
Oh, yeah, you're right. I should. How do I put my hand down? Put down action. Oh, it has here lower hand. Okay, hand is gone. Well, good to talk to you. Even if it was sort of by mistake.
Yeah, no, that's fine. Good to hear from you as well. So has everyone got a chance to sign up for one of the discussion breakouts? I see a few names in there. So
I'm guessing that there might be people that just jump on in the moment.
Right. Yeah. They don't necessarily want to commit to one session, but
yeah,
I don't know.
But your prompt is working. I think people.
Yeah, it seems to be doing stuff. The anonymous Wolverine was jumping in. So
yeah, and she even put a little smiley face. So.
I will just test my slides. That's okay.
Yeah, go ahead.
I don't know if I can stop sharing.
Yeah, somebody is Todd sharing right now?
I expect he is.
Okay. He just ended. So go ahead, Lorenzo.
Okay. I think it's working, right?
Yeah, looks great.
Okay, perfect.
Yeah, well, hopefully our next meeting will be in person. How are you doing, Cece?
Pretty good. How are you?
Okay.
Yeah. I keep thinking that everything should cool off a bit here. We just had graduation last week, but
yeah,
catching up on the last minute things.
Did you have graduation duties? Did you have like any graduate students or?
I went to graduation for the first time ever. And it was the catch-up graduation for the last 2 years when it was canceled. It was really fun, actually, because it was much smaller. You know, the main one was 50,000 people.
Yeah.
And the catch-up one was about 4,000.
Yeah. My nephew graduated in the main one. So
Did
get
your
to be
family
a
go?
flag bearer, you know, so he for arts and sciences, I think he carried in a banner because he's, yeah. But and my daughter Anna is there now as a freshman. So
At UW?
yeah.
Oh,
Yeah.
wow. What's her
Maybe
major?
maybe you'll see her. Biology is her plan, with probably a minor in chemistry. So we'll see.
That's
Right,
great.
she just finished her freshman year. She loved it. So it's great. She just got home 2 days ago because she drove back with a friend. So
Oh, I'm glad it was a good experience. It's been a weird year. But
yeah.
less weird than last year.
Yeah. It's slowly easing into less and less weird over time. Yeah. That's probably true for you too, Hansi. Was you Vic online in the fall, or did you guys go back all in person?
We were in person in the fall, and then in the spring, we were kind of online for a bit and then in person. And yeah, it's been like really confusing, right? Yeah, like nothing is really consistent in terms of like, what is the relationship between being online or not versus caseloads and, you know, hospitalizations, et cetera. Like it seems to literally have no rhyme or reason. So yeah.
That sounds like a prediction problem.
It does. It sounds like literally, you know, people could make a model and make, you know, like actual good decisions about these things, but you know, I'm not in charge, so.
And they don't have physics, you know, so bummer.
Oh.
Yeah.
Just a lot of data.
So Cece, brace yourself on this one. My son is going to be up the road from you in Vancouver starting in the fall.
Oh, wonderful. Congratulations, both of you. That's so great. I hope to see you both a lot more then.
So Paul, was the not yet in the chat in response to Hansi's not running things? Give it a little time.
And the world will be a better place.
It will. I'm all for Hansi running more things.
Aw.
I learned. I will share that she does say yes when you ask her to run things. So word is out.
Oh man, Paul, don't widely advertise these things.
I'm so mean.
I know.
I'm so super mean. Really sorry, but I'm so thankful that you agreed to lead our Canadian working group on atmosphere-related research. So to help with that leadership, it's great.
Yes,
Said yes to helping run the Polar Climate Working Group too. So.
Yeah.
Yep. Lots of things to run, y'all. Yeah, okay. I know. It's very interesting, actually. We've never done this experiment of like, if you had scientists running everything, like what would it be like, you know, versus like politicians? Like, would that change anything? Yeah. Anyway, okay. So thank you all for being here. And it is now time for us to resume some talks. And then after that, I'm super excited about all of these working groups or little breakout groups that we're going to do. So to begin, we will have Lorenzo Zampieri. Did I say that right? I hope I said that right. Okay, awesome. Tell us about clear sky biases over the Arctic.
Yeah, I was muted. Now you should be able to hear me. Okay. Good morning, everyone. My name is Lorenzo Zampieri, and I'm a postdoc here at ANCAR working with Marika Holland. And today I will talk about reanalysis. It's not really 100% related to CSM, but we all use reanalysis to verify our models or also as baseline for our analysis. And most of us use them as boundary condition for running single model components. And I will try to explain how we can improve the atmospheric reanalysis over the Arctic sea ice, really close to the surface. So yeah, this is what I will try to explain in the next 1 minutes. So the shortcomings of the current generations of reanalysis, in particular of the temperature field, the causes and the consequences of these issues, and what we can do for improving things. Yeah, just as a side note, this work is available as a preprint. So yeah, if you want more detail, please have a look there or just drop me an email. I'm happy to discuss further with you. So let's start with a very short historical overview. So when scientists started to run global sea ice and ocean simulations, they of course used atmospheric reanalysis as boundary conditions. And they realized almost immediately that the sea ice simulations was not very satisfactory. In particular, the Arctic sea ice tended to be too thin. And they found a workaround to solve this problem, which was to apply some offsets to the either temperature field or the radiation. And this has been done consistently in the past years for core forcing, GRE55, ERA5. Otherwise, we don't really get a good sea ice simulations if we don't do that. And if we jump of 15 years, this paper was published by Batrak and Müller, where they identify the issue with atmospheric reanalysis, and they link these biases to the missing representation of the snow over the Arctic sea ice in the atmospheric models used to produce the reanalysis. So what happened is in practice is the following. So here we see the sea ice representation in a typical CMAP model, can be CSM, for example. We have a thickness discretization. Over each thickness classes, we have snow, which has a very low conductivity, thermal conductivity. And so in general, when we couple this to the atmospheric model, the model has a good idea about the heat fluxes, and I would say they are quite decently constrained. On the other side, if we look at an atmospheric model used for the reanalysis, the representation of the sea ice is very, very simple. So first of all, we have a binary sea ice cover. We don't really have the concept of sea ice concentration. We have constant thickness everywhere in space and time, no matter the season and the location. And also, we don't have the snow layer on top of the sea ice. So we miss this insulating layer, and therefore the surface tends to radiate, and we have temperature biases. And yeah, here is just an example. In ERA5, we have an assumption of 1.5 meter thickness for the ice. In GRE55, it's 2 meter thickness. And yeah, the mechanism behind this bias is the following. So on one side, we have the reanalysis sea ice, which is constant thickness. If the real world sea ice is thicker than that, then the reanalysis will be too warm. So we have a positive surface temperature bias. On the other side, if the reanalysis sea ice is thicker than the real world sea ice, we will have a negative temperature bias. And when I'm considering thickness here, I'm also including the effect of the snow for simplicity. So it's the ice thickness equivalent, let's call it. Now, if we have a look at the temperature biases by comparing the reanalysis to real observations of the surface temperature, we see very striking results. So here I'm just considering a random day. We have ERA5, GRE55, and here we have the observations from basically a thermal sensor on board of a satellite. And you can see that we have positive temperature biases up to 6 degrees or even larger in some locations. And we also see that this bias is not really constant everywhere. It's very heterogeneous. And of course, if we apply then this forcing to as boundary condition to our model simulations, we will have issues and the ice will be definitely too thin. Yes, just a bit of a technical consideration is that the cloud state is relevant for this study, and for two main reasons. So on one side, clouds basically mask the sea ice, so the satellite observations cannot really see the surface when there is a cloud. They measure the temperature of the top of the cloud, and therefore we cannot really trust observations in cloudy conditions. And also when we have clear sky conditions, so when we don't have clouds, the bias tends to be particularly enhanced because in these conditions, the surface can radiate much more effectively to space, in particular during winter. And yeah, so we need somehow to identify the cloud conditions from reanalysis, and we do this in two ways. So here you can see for the same day, the total cloud cover in, again, Era 5 and GR55 and the long wave state. And you see that even though they refer to the same atmospheric state, they are very different depending on the reanalysis you're looking at. And therefore, we use the long wave to diagnose the cloud state in Era 5 and the total cloud cover in GRA55. And we found that this is a reasonable approach for these two products. Now, how do we formulate an effective bias correction strategy? So what we want to do basically is to have a correction which is a step forward compared to the previous attempt. So we don't want something climatological that's applied everywhere, but we want a correction that's state dependent. And the first step is to quantify the temperature bias at the daily time scale when we have observations. And we can do that because we have quite good observations nowadays of the surface temperature from remote sensing products. The second step is to identify some predictors that we can associate to the bias. Of course, we could develop a correction that relies only on observations, but the problem is that observations don't go back far enough in the reanalysis record, and they are not available everywhere at every time. So we need to have some more reliable products that are based on reanalysis, on atmospheric reanalysis and sea ice reanalysis that inform us on the nature of the bias. And here we use the surface temperature itself, the downward long wave radiation, so that gives us a good idea about the cloud state, and also some sea ice information, so the sea ice thickness from biomass and the snow thickness produced by the snow model, the Lagrange snow model reanalysis. And then the third step is to have a neural network, which is basically a model that connects those predictors to a correction, a local correction to the bias that we apply at every time step, basically at every grid point. So here you can see basically a general view of the bias and of the correction predicted by the neural network as function of the four predictors. So we have the temperature, the downward long wave radiation, and here on this plot we have the sea ice thickness and the snow thickness. And we can see that the structure of the bias somehow makes sense. So we tend to have the strongest bias in colder regimes and in clear sky regimes. And also we tend to have this form bias over the thicker ice, and that works well with what I explained before. And at the same time, we have this negative bias over the thinner ice. So we have this two type of regimes, and you can see that the neural network is able to capture well this bias. And yeah, just for reference, this data was not used in the training of the network. So it's sort of an independent comparison. But now let's have a look at how the situation looks like when we look at maps. So when we apply our correction at the reanalysis timescale, so 3 hours for GRE55, 1 hour for R5, and then we take the average over almost 40 years. We see that the correction that we get as a structure, so it tends to be stronger over thicker ice, and this makes sense. And also we see that in particular in winter, we have this double, like we have this negative correction in the Central Arctic where the ice is thicker than the reanalysis assumption, but also we have this positive correction where the ice is thinner than the reanalysis assumption, and this makes sense, and it's quite convincing. We also observe that there is a seasonality related with this correction, and this seasonality emerges from the model itself. So we didn't really impose it, and this is also quite nice because it means that the neural network somehow, even though it's not really physically informed, but it can, it can produce a physically meaningful correction. So let's have a bit more a detailed look into this seasonality of the temperature correction. So here what I'm showing is the average correction north of 70 north. So it's the difference between the original and the corrected reanalysis field. And we can see basically the annual cycle split it into 4 decades. And we can see that, so first of all, in summer, we don't really have a correction on the temperature field. And this is because we basically have temperatures that are close to melting. So yeah, we don't really have a bias in the reanalysis. We see that we have, in general, a maximum when the temperature are the coldest during winter. And also we see that we have a decrease in the strength of this correction with time. And this makes sense because we can think that the current sea ice conditions are more compatible with the reanalysis assumption compared to the sea ice conditions that were observed in the 80s and in the 90s. And we see that, yeah, this structure is consistent, I would say, between ERA5 and GRE55, although in GRE55 we don't really observe this strong this correction trend, let's call it, in winter, but more rather in the fall during the freezing season. Now we also checked if this correction has an impact on the multi-decadal warming trend of the Arctic, and it has. So I would say it has a small impact overall compared to this strong signal that we see in polar regions. And in general, we can see that the corrected field tends to have a slightly larger warming trend. But yeah, I mean, I think it's, I'm not sure if this is really a significant result, but yeah, we will check this more in detail. So yeah, this brings me to a quick summary. So the correction is, first of all, state dependent, the way we developed it, and this is coherent with means that it's coherent with the observed sea ice conditions and with the local weather, and it also favors clear sky events in agreement with the observed nature of the bias. Also, the predictors that we chose are physically compatible with the mechanism that explains the bias, so they are somehow related to this misrepresented snow thickness and ice thickness. And also we are able to capture this positive and negative corrections depending on the ice state, which I think this didn't necessarily happen with previous correction attempts. And also a self-emerging property of the correction is that we have a seasonality, but also an interannual trend in the reanalysis, which was definitely not the case in previous correction strategies. And yeah, I'll leave you with these animations where we show how the correction looks like in a 1 hour time scale. So when it's applied on the RFI field. And yeah, you can see, of course, that it's restrained to clear sky conditions. And you can see the effect, for example, of clouds appearing and disappearing. And yeah, we're not sure if this is a limitation of not of this method. For sure, the correction that we developed is consistent with the reanalysis field. Yeah, it might be not 100% compatible with observation, but that's something we will investigate also when we apply this reanalysis to run as boundary condition for sea ice models. And that's the next step. So thank you, and I'm happy to take questions.
Thanks, Lorenzo. Dave, go ahead and ask your question real quick, and then we'll leave the rest of the questions for Lorenzo on the chat. So please ask him on the chat, just because we're running just slightly over. So
sure, no problem.
Oh, okay. I think Dave's going to ask you on the chat. Okay. So I'm going to hand it over to Paul Kushner.
Thank you. Let's see. How's that working? Can you see my lead slide?
Yeah, looks great.
Slide view? Okay,
yeah.
Great. Yeah, so I'm presenting today on a project that is led by a PhD student in my group, Alexandre Odette, and also a new student, Luke Fraser-Leach. And Alexandre I'm mainly going to be talking about his project, and this is about looking at sea ice perturbation experiments. And it's outside a lot of what has been talked about today so far, but I'd really like to hear your feedback. So that's why I rather selfishly asked to come and talk to you. Just by way of introduction, this is a talk where I'm thinking about kind of idealized views of polar climate variability in the climate model hierarchy. And I think, so this is kind of a, maybe I think of it as an iconic figure. I don't know, I've seen it a lot, showing, sorry, my cursor has been lost. There we go. Okay. Nope, that's not helping. There we go. Can we see my cursor? No. Okay, I'll just go over here. Basically, we have this whole big model hierarchy, right, where we can try to model the Earth system with various degrees of complexity. I don't want to belabor this, but oh, this is terrible. Oh, there we go. Okay. What I'm trying to do here is talk about a particular set of experiments that play with the boundary conditions in climate models, where we go from a comprehensive Earth system model like CSM. We can remove the dynamical ocean, go to a slab ocean model, and we can go to a no ocean model, an AGCM, and replace the ocean boundary conditions and sea ice boundary conditions with prescribed fields. All right, so the project that I'm going to be talking about is the Polar Amplification Model Intercomparison Project, PAMIP, all right? This is a set of, it's a model intercomparison, it's a set of constrained sea ice experiments that are used to elucidate the causes and consequences of polar amplification. And there are PAMIP experiments that, in this sort of first group here, that looked at AGCM simulations and tried to understand the circulation response response to sea ice loss for understanding polar mid-latitude connections. But there's also a set of coupled simulations, and those are called PAMIP Group 6. Now, the PAMIP prescription it's inspired by pictures like these. This is taken from the earlier work from Clara Dester's group. Just comparing when you take a model like CESM4 and perturb the sea ice in it, either in an AGCM setting or in a coupled ocean atmosphere GCM setting, you get a very different polar response, right? You get a lot more warming, deeper warming, and in the slab ocean, there's some also dramatic differences too between the AGCM and the slab ocean. And basically, as you introduce more coupling, you get more thermodynamic coupling into the deeper free troposphere, and even coupling from the northern hemisphere to the southern hemisphere. So PAMIP is, I think, inspired in part by model experiments like this. And so what PAMIP does, so the group 1 experiments are kind of these AGCM experiments, and you impose a sea ice concentration change that looks like the map here in the upper right, and also a sea ice thickness change. And these perturbations, this is kind of important, they're drawn from the kind of an aggregate of CMIP5 sea ice changes under 2 degrees of global warming. And there's actually Arctic and Antarctic experiments that are part of this prescription. And these are all documented in the paper by Smith and others in 2019. So what we did, and what several other groups have done, is start to use these perturbations to force models. So this is an example of an AGCM experiment. Okay, the surface temperature response to that sea ice loss with radiative forcing held fixed. And here's an experiment with ghost nudging. So this is basically adding heat to the bottom of the sea ice. And looking at the responses in temperature and also in the zone as well, okay? And what you might notice is that in the AGCM simulation, using this particular forcing and model, so the model is the specified chemistry version of Wacom 4, so it's an older generation model, but it was good for this purpose, I think. And what we noticed was that in the coupled simulations, for some reason, we're getting unexpectedly weak warming compared to what we saw when we imposed sea ice concentration and thickness changes in the AGCM. And also the warming here is not quite as deep, and it's not quite as strong, and the Arctic amplification we get isn't quite as strong. So we were trying to understand this and the issue of method dependence. And so the research question here, it relates to this protocol. And I'm trying to make a very simple point, so I hope I don't make it too complicated in the talk. But basically, the PAMIP Group 6, this coupled protocol, it doesn't really prescribe a method for driving sea ice loss, because different modeling groups had different ways of approaching coupled modeling of prescribed sea ice. My own observation was that the PAMIP group, through its workshops, there weren't very many sea ice modeling experts in that. There were a lot of people interested in the atmospheric science and people who worked in sea ice prediction for sure. But in terms of really thinking about the protocols, I didn't hear those voices very often. So I think this is something that could be improved on. And what we were thinking about was the method dependence of the responses, all right? And certainly if there's differences in the Arctic responses, then we expect differences in the extratropical and tropical responses as well. And there have been studies by James Green, by Lantau Sun, that have looked at the method dependence in these coupled model experiments. So what we were trying to do is develop a standard method that could be easily implemented and by various groups to control sea ice a bit more carefully. And what kind of results we might get from that. And we have the PAMIP specifications that to go by. And the final question is actually a bit more of a follow-on research question, and that is whether we're doing the right thing by running these perturbation experiments at all. So I'll try to get to that here. So first of all, I'll just describe this method. So Alexandra's calling this the hybrid nudging method. And basically, we have this target, which I've shown you before. And the standard ghost flux nudging method, this is what was used in several papers. Lantau Sun had a bit of a review of this in a short paper of different methods. Kelly McCusker used this in her work. And the idea is it's a basal heat flux that you add to the bottom of the sea ice model, and you can use that to thin and thicken ice in all categories. And the little tweak we've introduced here is to apply some nudging to the concentration, but to focus first on the thinnest sea ice category available in the grid cell. So that's where we'll do our concentration nudging. Alexandra adjusts for salt conservation just to make sure that we're conserving water. We're still adding we're still nudging towards a target thickness. And so we're using both these targets at once. Whereas the ghost flux nudging is focused on sea ice volume or like the sea ice thickness for all categories. We're trying to sort of separate out the thickness and the concentration nudging. So as I said, it is a simple idea. There's nothing, it's not rocket science, but it's just checking if this helps or not. And so it's a hybrid because it's a combination of a sea ice specification, which kind of gives a jumpy sort of nudging from time step to time step. And that's been used in some experiments from other modeling groups, and using the thickness nudging, which tends to have nice smooth behavior over time. Okay. Alexandra did some tuning of this, so we can look at the RMS error as a function of the sea ice concentration timescale and sea ice thickness nudging timescale. And what you'll find is if you go to very short nudging timescales, you'll get the target field right. Okay, so but somewhere in the middle between sort of just a few days and many days for sea ice thickness, and we actually looked at very short timescales for the sea ice concentration. You can kind of rank the responses and your ability to have a relatively less bias and better lower RMS error. And basically, Alexandra hit on this combination of parameters for this particular SC Wacom 4 set that he hit on. So this is a 1 day sea ice thickness, sea ice concentration nudging, and a 5 day sea ice thickness. But results may vary if you're doing this with your own with other models. So that's to be determined. But and these were all 10-year simulations, so it's nice to have a relatively coarse resolution model to work with to do some of this work. And I just should mention that he also did this with SICE standalone and got pretty consistent results, and in the Antarctic as well. So the bottom line is shown here in terms of like the overall impact. So the key thing about all these methods is that they really do get the volume right. So the effective thickness, or the average thickness over the Arctic. The target is an X's here. The solid is hybrid, and the dotted is the ghost method. The ghost method. So that's the older method. And the gray is control, and the warm climate or the sea ice perturbation climate is in purple. Okay. What you find is that the hybrid method is better able to capture the seasonal cycle of the thickness and its response and that's important, and also for the total sea ice area. All right. So the key thing is that the ghost nudging method overestimates the summertime sea ice minimum in the control simulation, and it underestimates the wintertime melt under 2 degrees of anthropogenic global warming. All right, and so we're trying to, and when we do this nudging to the thinnest sea ice, that helps us get kind of a capture that target with a relatively light nudging and capture the full PMF target. And it's all connected in a sensible way to the surface energy budget, and there's some figures about that in the publication, or in the paper that's in review. So what does that do to the response? Okay, so here's the AGCM response I showed you before. Here's the response from the nudging experiments. I also showed you this before. And here's the results from the hybrid nudging. So when we focus on nudging this thinnest sea ice, and of course we're nudging marginal ice more favorably with this 2 degrees of warming kind of perturbation. We get additional warming through the Arctic and this is not an observational target. We're just kind of trying to capture what we typically see in these coupled simulations, and actually quite a deep warming in the zonal mean. All right, and we find some interesting results too for Antarctic, which I have in the extra slide, but I don't know if I'll have time to show it. All right. And there was one mystery in this, and which is why we weren't seeing a strong response from the ghost nudging that matched previous publications, when we're basically just using the previous methods like Landau's methods. And the fact is that the 2 degrees of warming sea ice perturbation, that's actually relatively weak forcing compared to end of century forcing for these simulations. And so we actually are able to recover a deeper warming when we use a stronger sea ice forcing. But if we're trying to capture the PAMIT protocol, which is, which a lot of groups have worked on already, and is already approved as a project, we found this sea ice concentration nudging method worked better. So the quick question I want to sort of address before concluding is just to ask, well, are we on the right track with these sea ice perturbation experiments at all? And the paper that I'm worried about, and we've been talking about in the group quite a bit, is a paper that's in review by Mark England and others. And Mark has been talking about this paper in PAMIP workshops and other forums. And what they're saying, this is what work with Ian Eisenman and Wagner as well. And what they're saying, and this is a result that they showed within the context of an energy balance model, and we've reproduced the results. It's pretty simple to do so. And so if this is the result in temperature at the surface for typical global warming experiment under radiative forcing, just an idealization in an EBM. What they say is that the actual sea ice effect can be constrained by just looking at the top of atmosphere top of atmosphere energy balance. And if you prescribe the albedo, the planetary albedo change in that setting, you get a certain amount of warming that can be attributed to sea ice loss, but it's much less than what you get when you run a typical sea ice perturbation experiment. So what Luke has done here is do a bunch of different nudging experiments, albedo experiments, and so on. And their point is that basically this is a seasonal cycle of the response. And the idea is that if you try to target a certain amount of sea ice loss in a simulation, you're going to have too much albedo change in these perturbation experiments. And that will lead to too much polar warming, and overemphasizes the role of sea ice as a trigger of polar amplification, and it might mask other effects. And that's basically what's shown here in this is in the seasonal cycle. Basically, the specified albedo simulation, which is the one where you figure the top of atmosphere albedo change under global warming, that actually doesn't give you enough forcing to retreat the sea ice to the value that's seen under, say, doubled CO2. But if you use a nudging, you get that target, but then you get too much warming compared to what's sort of realistic according to the energy balance argument. So that's kind of a bit of a cloud on the horizon, and I think it's worth thinking about. So just to wrap up, we're proposing a simple hybrid sea ice nudging method to better explore coupled ocean atmosphere responses to sea ice loss. And so we're trying to target both the concentration and thickness at the same time in the PAMIT prescription. And Alexandra's been looking at this for looking at different models and looking at poleward heat transport as a kind of scientific focus. And we see a very strong dependence of the results in these coupled simulations on the sea ice constraint. So we have to be careful on how we do these experiments, which are very expensive. And there are concerns that these experiments drive spurious polar amplification, and those concerns I don't think shouldn't be ignored. There are cause for concern. Thanks.
Thanks so much, Paul. I think let's have one question on the floor and then maybe the remainder of the questions in the chat. Does anyone want to ask a question to Paul? It looks like Dave has a question. Dave, do you want to ask a question?
Sure. I mean, one of the issues I've talked with Len Tao a lot about this is just how do you apply this nudging over the subgrid scale ice thickness distribution? Do you just apply it evenly into all the categories, or do you just resort back to a single category?
No, so well, we do different things. So for the concentration, we nudge concentration starting with the thinnest sea ice category, right? So we sort of use up or increase the thinnest sea ice category. So we're selective there. But for the heat flux, we just try to copy Lantau's method, or which is not his originally. I mean, it's the one he's been using, and we used we're drawing from his code, and then we just apply the heat flux proportional to the amount of thickness in each to the amount of sea ice in each thickness category. But it's the same. Yeah.
Thanks so much, Paul. It sounds like Paul wants a lot of feedback, so please continue to give Paul feedback within the chat. And we will move on to our next speaker. And our next speaker is Patrick Ugrenau.
Yes, let me set everything up. I believe someone's still sharing though, so we can't.
Oh, Paul, would you? Yeah, thank you.
Thank you. All right, can we see everything?
Yep.
Great. All right, so good morning. My name is Patrick Ubernow. I am an undergraduate student at the University of Colorado Boulder. And today I'll be talking to you about a little bit of my college undergraduate research that I've gotten to participate in. And we're focusing on the North Open Water Polynya and how it's going to respond to a warmer climate. So with a little bit of background information, what is the polynya and why it's important? So our North Open Water Polynya is located in northern Baffin Bay, just west of Greenland. And on average, it's approximately 80,000 kilometers squared at its greatest extent. And by definition, a polynya is an area of open water surrounded by sea ice. And our North Water Polynya supports a vibrant marine ecosystem here in the Arctic. And in this image, it's just a kind of a reference to see where our polynya is and what it is. Additionally, local communities do rely on this ecosystem as a form of sustenance as well. So understanding how global temperatures, a rise in global temperatures will affect our polynya is vital to the future of this ecosystem. Okay, so we looked at two data sets to actually capture our polynya, and we utilize CESM1 and NSIDC data in order to, and we plotted that here in our seasonal plot of area. And we could see both capture it fairly well in similar fashions too. They both model the polynya opening in the same time, peaking and dissipating at the same time as well. And we can see that here as well. They both model it in slightly different fashions, but both capture it very well. And how we actually calculate the area of the polynya is we defined a polynya region, which is this red box here. And we summed grid cells that were below 70% sea ice concentration into the total area within this region. And the black contour line is actually our 70% concentration line. So this dark blue is what's being added into the total area in both of these spatial plots. And you can see why the area is varying a little bit between the CESM and NSIDC, as our observational data actually models it forming further south, while our model sees it forming further east instead of south. So additionally, in order to calculate the area, we utilized a flagged region in eastern Baffin Bay as well. And this flagged region is this orange dashed box right here. And we utilize this flagged region to identify when our polynya is no longer surrounded by sea ice, but rather when it connects to those waters in southern Baffin Bay. So there's multiple thresholds that we can utilize for our flag. And here's just an example of a few of them that we looked at. And an interesting note is that we find the threshold we use for our flagged region doesn't affect the opening of our polynya, as each seasonal plot captures it opening in April approximately. Though the flag does highly affect the peak of our polynya and its dissipation, as can be seen throughout these 6 subplots. So we know how we calculate area. So we'll get into how the polynya is actually changing as temperatures increase. And we looked at 3 warming levels to actually determine what is changing. And that includes the 1.5, 2, and 4 degree Celsius scenarios. And as these temperatures increase, we found that our polynya opens up earlier So it's forming earlier and dissipates sooner. And when we say dissipate, we just mean that it's no longer surrounded by ice and it's connected to waters in southern Baffin Bay. So here, looking at our seasonal plot, we'll focus on its earlier dissipation first. Historically, we see that our Polynya is present in July at approximately 30,000 kilometers, give or take. Though as we hit the 1.5 degree warming scenario, we see that it decreases drastically to nearly 5,000 kilometers squared. And if we already hit the 2 or 4 degree warming scenario, the Polynya is no longer present in July and is really just open water. And we can see that here in our spatial plots. Our flagged region still has large ice concentrations within it, keeping it the Polynya isolated. And additionally, we still see somewhat of that same concentration here. But as we get to the 2 and 4 degree, and especially in the 4 degree, we can see that sea ice concentrations are they're not even present in the 4 degree warming scenario, which is showing how our Polynya is completely gone and it's just open water by July. Okay, so we focus on dissipation, its earlier dissipation, and we'll focus on now on its earlier formation as well. And this is the same seasonal plot from the previous slide, but we just zoomed in to really capture what was going on. And when we look at April, historically, we see that the Polynya is just starting to form. It's approximately 1,000 kilometers squared. And we can see that here along the eastern portion of our Polynya. It starts to form a little bit right here, maybe a little bit on our western edge. It's just barely present, a small opening in the ice. Though, as we hit the 1.5 or 2 degree warming scenario, we see that the Polynya is nearly 3 times larger in size in April at about 3,000 kilometers squared. And we can see the signature a bit stronger now as it's starting to open up a little more along this eastern portion and maybe a couple spots on our western side as well. And really, we really see a big change by the 4 degree warming scenario, where it's nearly 5 times bigger than historical data. And it's a very strong signature. We're starting to have a very large opening within the ice in April now, and especially in a couple spots on our western side of our Polynya as well. So we know how sea ice concentrations are going to be changing and how global temperature increase is going to affect our Polynya, but we also want to look at ocean conditions as well. And specifically, we've looked at mixed layer depth, and we utilize the same 3 warming scenarios, the 1.5, 2, and 4 degree scenario for mixed layer depth as well. And in this seasonal plot, we can see that the mixed layer depth increases drastically in the early months the Polynya is open. If we just look at May, for instance, we can see it nearly increases by 50 meters depending on the scenario that is met. And additionally, we note that the mixed layer depth is most shallow after our Polynya dissipates. So as soon as our Polynya connects to open waters, which tends to happen in July as temperatures increase, we see that mixed layer depth decreases drastically to nearly 10 meters in depth in July. And I should note that this is a seasonal plot of just 1 grid cell within our Polynya, and it's just a rough estimate of where we are on this image. It's 76 north and 285 east, but you'll see that better in the next slide. So we have the same seasonal plot of that 1 grid cell, and that dot in each of our spatial plots represents that 1 grid cell. And very quickly, we notice that the mixed layer is deepening and this deepening is greatest on the western side of our Polynya. As you can see here, this dark blue signature is about approximately 30-40 meters in depth. But if we were to hit that 1.5 degree warming scenario, we see a drastic deepening. And deepening is largest, we noticed, when we limit warming to this 1.5 degree scenario. Though under greater warming, and especially in the 4 degree warming scenario, we note that mixed layer depth becomes much more uniform throughout our polynya and in Baffin Bay as a whole. We don't see as much spatial variation as we did historically. Now there's really not much change as we go east to west or north to south. But yeah. So in summary, we'll just cover the quick key points. The North Water polynya, we expect to form earlier and dissipate sooner. And the timing of our polynya peak and dissipation depends highly on how we define our polynya. And specifically, this refers back to the Eastern Flag region and what threshold we utilize. Although, again, we did note that regardless of what threshold we use for the Eastern Flag, it does not affect the opening of our polynya, the timing of the opening of our polynya. Additionally, we looked at mixed layer depth, and we noted that it's projected to increase drastically early in the year. And we saw that up to a 50-meter increase is expected along the western side of our polynya if warming is limited to 1.5 degrees centigrade. Additionally, if we continue on through those warming scenarios and hit a 4 degree scenario, we saw that mixed layer depth becomes more uniform throughout our polynya and Baffin Bay as well. That's the extent of what we've looked at currently. But we are currently looking at vertical velocities and biological productivity in our polynya region as well. And we're trying to understand how these other ocean conditions are changing, as these are the key characteristics that support this vibrant marine ecosystem. So understanding how these ocean conditions are changing as well will give us insight into how this polynya and how this ecosystem will be affected as global temperatures increase. But that's it. I'll try and answer any questions you may have.
Thanks so much, Patrick. So I can see that Dave has a question. Dave, do you want to ask your question?
That's fine. I just noticed that we're over into the discussion time. So
yeah, just barely. Okay. Okay, Patrick, go ahead and take the questions on the chat. And thank you so much for your talk. And now let's see if the breakout rooms are available. Oh, they are not yet available, maybe. Let's see.
Just a sec, I'll open them now.
Okay. Thanks, Todd. Wait, are there 29 breakout rooms? Oh, okay. There's people not assigned. I see. Okay, so we will head into the breakout rooms to discuss sort of future directions for the Polar Climate Working Group and where our interests lie in terms of our scientific objectives. So looking forward to talking to y'all.
Please let me know if anyone needs help entering breakout rooms.
Hey, Todd. If you hear me, could you put me in the same breakout room as Betty and Bill, please?
Gunter. Was that you or is it someone else?
Yeah, it was me. Sorry.
Okay. I thought I recognized your voice, then I wasn't sure. Okay, so you want to go to which room? What's the name of the room you'd like to go to? I'm not hearing you. Oh, you're on mute.
Oh, sorry. Can you hear me now?
Yep.
Could you put me in the same room as Betty and Bill?
Just tell me the name of the room.
It's multimillennial ice sheet modeling.
I'm sorry.
Multimillennial.
Sorry, what's the name again?
Multimillennial ice sheet modeling.
Is that long IS modeling? Yes. Okay.
Oh, okay.
Okay, you've been assigned there, so you should be able to press the breakout window. Good, great. Okay, anyone else need help going to a breakout room?
Well, that was an exciting discussion. We all got like just shoved into here when everyone was mid sentence. So thank you all for that exciting session today. And I think that we are just about ready to wrap up, unless there's any final thoughts that any of my fellow co-chairs or anyone else wants to contribute. And then I think after this, we are all planning to perhaps go find some lunch or snacks to eat, and we might join up again here just for some catch up.
Yeah, so I'll just say thanks also to everyone, and thanks for the great discussion, and at least, you know, the co-chairs all and other people that were sort of in the rooms overseeing the discussions will coordinate and get kind of a group input that'll inform our computing proposal and other things moving forward. And hopefully some of you stick around for lunch too.
Yes, thank you all so much. Hopefully we'll get to see each other in person sometime soon. So
it does look like they're keeping this Zoom session open for the lunch networking. So
great.
Yes.
So you
So
can
I
just
think,
stay on, yeah, if you'd like.
yeah.
Okay, back in about 5:10.
Thanks everyone.
Thank you all.